First, I want to remind everybody that when I when I do these Zoom meetings, I always post them on my YouTube channel in case anybody misses the actual Zoom meeting. So if you have any objections to your name, or perhaps occasionally people will actually show their face and it ends up on my YouTube channel. So if you have any problems with your name or your face or anything being posted on my YouTube channel, you need to let me know via text or email immediately or as soon as possible. I'm not sure how I'm going to edit it. I haven't had to do that yet, but I'm sure I'll figure out some way to edit out the parts that any student objects to having put on the internet. So just let me know if you have something. I'm going to make sure try to make sure everybody is not endangered in any way or something like that. So if you have any problems, remember to let me know. And of course, that's true for all my physics classes. Every time I do any Zoom meeting, I post it on the internet like this. So in addition to that, we are going to do a little bit of prepping for the lab, but I decided to give you, a good fraction of the time off so that you could actually do the lab on your own to some extent. And over the weekend, or actually just before the weekend, I went ahead and opened up the discussion boards on Canvas so that you guys could actually communicate with each other through that portal if you wanted to, in case you need to work on, for instance, homeworks together or labs together. And I explicitly tell you that's okay. You'll see there's one for homeworks, there's one for just general course stuff, and then there's one for well, actually, I think it's one for physics problems, period. So that's not just homework, but anything. And then there's one for labs as well. So y'all can prepare to meet like that, or you can make up your own meetings between you and the other people in your lab group. You could use this time to communicate with each other, or you could use the Zoom portal to, or excuse me, the discussion board portal to communicate with each other. I know one student just came in that hadn't been in yet, so I just want to remind everybody to chat me your first and last name if you haven't done so already. That's your attendance for today. And again, if you have any problem with your name or your likeness, your face, or anything being posted on my YouTube channel, you need to let me know via email or text message ASAP. So, uh, as I said, our class is supposed to start at 9:30 in the morning, and I gave you until 10:30 to give you extra time, and I made sure I actually had the lab stuff out by 9:30 and sent you an announcement, just making sure people could start if they wanted to. So I'm not planning on spending too terribly much time on giving you time for the lab. I think that's something y'all can do. Ideally, I want you more or less to do it on your own, but I want you to feel okay with communicating with other students. It's not like I'm trying to get you to do it on your own because of a cheating issue. It's more because I want you all to think about these processes and having uh, given the fact that you've already experienced the analyzing motion labs, I think the motion detector lab will be quite a bit easier now. In fact, if you do it the other way around, the analyzing motion lab's a lot easier than the motion detector lab. So it really is whichever one comes second is a little easier, so you shouldn't have any problems. Remember those four major questions I told you in the analyzing motion labs? Which was on a position versus time graph. What exactly does the height of a point on the graph above the horizontal axis? What does that mean? And of course, in the position versus time, you don't have this on the motion detector, but you possibly could in analyzing motion labs. But also, if the graph is down below the horizontal axis, what's the distance down from the horizontal axis to a point on the graph mean? So that's one of the major questions you need to be able to answer after completing these two labs. Another one is on a distance versus or position versus time graph. What does the slope of the graph at any particular point mean? What about the steepness of the slope? What about if the slope is steep and positive? In other words, it's a high slope and positive. Or how does that compare to a positive low slope? In other words, a gradual incline as opposed to a steep incline. What about a large negative slope compared to a large positive slope? What about a large or small positive slope compared to a small negative slope? That's all with regards to position versus time graph. So those are, the two major questions that you should be able to answer, and then answer those same questions for a velocity versus time graph. And in principle, you could do it for an acceleration versus time graph, but we don't really study that because all our accelerations that we study, at least in lab, are generally constant acceleration, except for when we study harmonic motion and, mass on a spring or a pendulum on a bob or something like that, or a bob on a pendulum or something like that. So keep those questions in mind. Remember, at the end of the analyzing motion lab, which is supposed to be due by midnight tonight, it's normally the scenario because it's always 1 week from the lab date, which normally would mean at 9:30 in the morning. But since some people might not have attended the lab last week, which was online, I allow it till midnight. And then not only that, in case anybody had any problems, I told you you can automatically go another day if you need, without any deductions in points or anything. So if y'all still need a little bit more time, y'all need to work with some of your lab partners on the analyzing motion labs. Y'all need to ask questions or figure some stuff out. Y'all still have at least another 24 hours or so. Actually, let's go ahead and make it till Tuesday. Yeah, that's tomorrow. I'll just go ahead and make it till Tuesday at midnight to get that done. And to be honest with you, the way it normally works is if I don't grade the lab before you turn it in, and then you turn it in, even if it's a little late, uh, I usually don't mark off for it because, you got it in before I graded it. But I always, always, always take off for it if you get it in after I grade it. So don't use that as a crutch. Use that when you need it, occasionally, but hopefully only once in the whole semester. But this time, like I said, I'm giving y'all another chance in case you had any difficulties with the downloading of the software or downloading of other software or finding other software to use for the analyzing motion. So. Anybody have any questions on that before we move on? All right, let me make sure my computer is on the appropriate screen, the one that I need, and pull it up to the appropriate spot. Yeah, I guess this is good enough. And then I will go ahead. It looks like no one had any questions on the chat board either. So I did see a couple more people come in. If you came in late, you're supposed to chat me your first and last name if you haven't done so already. We are going to talk about lab for this week, and then I'm going to do a little bit of time on that. But from there on out, I'm just going to use the time to cover Chapter 3 material, and then let you guys go on and either communicate via Zoom on your own or communicate via discussion boards on your own. Y'all can group up with your normal lab partners. That's fine. You can group up with someone else that happens to be in your lab. That's fine too. Again, I want you guys interacting with each other. That's it's not just the social part of the lab, it's actually the helpful part because inevitably each week you'll have a person that understands the lab a little better than the other people, and that person can be helpful. And not only that, that person's not always the same person every week. A lot of times it is, but a lot of times it's, you've ran into a niche area where the student that didn't necessarily understand stuff in the past is like, oh, I got this. And that's a good thing for everybody that's experiencing it. So make sure y'all do that. Make sure y'all communicate with each other. Make sure you ask me questions if you have any. I'm going to go ahead and share my computer screen with you, specifically the window with our Canvas page on it so I can show you what this week's lab is. So let me do that real quick. I just put it here, but it does not look like it's showing the appropriate one. Why is that not an option? Okay. Oh, there it is. So I'm going to kill this real quick and then try it again. Sorry about that. Now I got it. Okay, so this is our course PHY 241D01B. As you can see, these are all our modules for the course. And this is the way, by the way, in case you guys are not getting it, and especially for my online students, this is the way I expect everybody to go about doing their coursework. So anything that you might see that comes available because you're using some other parts of Canvas than going straight to these modules, I don't necessarily even know they're there there. So if you see some assignment that's due, but it's not in one of these modules, that's sort of the whole point is if it's not in the module, you ain't got to do it. Okay. So apologize for my bad grammar, but that's the main thing. All right. So here's week 3, which we did last week, and here's week 3 lab module, which we did last week. Uh, I'm going to kill these because we don't need them now. But what we're doing this week is week 4. This is the actual topic of the lecture. As I told you guys, I would be separating the modules into lecture material in one module and then lab material in the other. This one has a lot of stuff in it. It's not normally like that, but one of the most important things that you learn in Physics 241, as well as the algebra-based physics class, is vectors and vector addition, making vectors out of descriptions, making vectors in a coordinate system, and then breaking those vectors up into components in those coordinate systems and adding those vectors, being able to subtract vectors, being able to multiply vectors by scalars, being able to take dot products of vectors, be able to take cross products of vectors, be able to differentiate vectors, be able to integrate vectors, all that good stuff. And therefore, I wanted to make sure you had access to a lot of stuff. So you'll see on here some of the stuff I'm getting ready to cover. You'll see a previous lecture back in January 24. Here's another one from September 23. But here's a short video on adding vectors by drawing, which is what we're pretty much going to start off with in discussing it. Subtracting vectors by drawing, that's another thing that's important, and I'll show you. And then vector addition part 1, part 2, part 3, part 4, part 5. This just shows you a step-by-step, video-by-video process in which you can take the various ways I specify vectors and learn how to break them into components and then how to actually ultimately add them. You'll see quick vector addition. This is, again, another quick and dirty video for just how to add vectors. World's greatest vector addition problem. I specifically say that not because I'm under any delusions that I made something that's the best, but because it sort of is a vector problem where I show you all the different ways that I could specify magnitude and direction of a vector, and then I break those vectors down into components, and I add them one by one by one, and then I find the magnitude and resultant of the vector, or the magnitude and direction of the resultant vector, and so on and so forth. There's a lot of other problems down here, as well as once we get out of the vector addition, vector subtraction stuff, we go into projectile motion, which is the other part that this chapter is about. So hopefully y'all can get all that. Here's the chapter 3 homework. I doubt it, but if we were to start chapter 4, I'd go ahead and turn that open as well. You can see this stuff isn't there. That's because instead of this week's module for lecture, I'm using this week's module for lab for the actual lab. So as I told you in the announcement that I posted this morning around 9:30, how to complete the motion detector lab. This is just a video from last year, or actually this is just a video from a couple days ago of how to do it. I forgot I grabbed the one from my online class. Here's the actual document that you'll be filling in. If you click on it, you'll notice it pops up a Word document, and then I can zoom in so you can see it. But notice these bold print things. Those are things you're really supposed to listen to. For some reason, I still get students that don't read this part. It says idealize your graph. So if you draw a crappy graph like that, or specifically if you make a crappy graph like that with the motion detector, which you guys aren't doing because you're not actually using the motion detector equipment, but we have made the graphs for you. If you see a graph that looks like that, your job is to idealize it. So, this little hiccup right here, you could tell was probably from when we first started moving something or something like that. And you can tell we sort of tried to do something shooting up and to the right. So this should be your representation of that one. Similarly, we had to bring something up to some set speed, but it looked like mostly we were trying to draw a horizontal line, or trying to make a horizontal line with the motion detector. So that should be represented by a horizontal line on velocity versus time. Remember, pay close attention to your axes, because d versus t means something entirely different than v as in velocity versus time. Don't write numbers from the axes on your idealized sketches. You're only looking for trends and relative steepness of slopes. I agree that you don't need to do that, but feel free to do it if it makes it easier for you to clarify what you're trying to specify. So sometimes if you're trying to show a really, really steep slope, but you accidentally, drew them too similar, well, first off, the best thing would probably be just to redraw it, okay? But if there's some reason where you can't, like you put a lot of work into that or something, and you still want to do it, then you could actually, label a couple points, put in their X and Y for each of the points, and then calculate the slope so you can see something like that, just so you can make it clear which one has a higher slope than the other one. I don't mind you doing that. It's just not. It's beyond what you were supposed to do, so you didn't have to. However, there's some graphs where they'll, or yeah, some graphs you're supposed to make where they tell you to walk away from the detector, stand still for 3 seconds, and then walk quickly back or something like that. Those are ones where it's really helpful sometimes to actually write in numbers. Like you might not write in the number 0 for 0 seconds, but the graph's going to look like this, and then it's going to sit still for a long period of time. You might call, when the horizontal spot started, you might call that 2 seconds, and then to show that you stood still for 5 seconds, you might want to put the other end and mark it as 7 seconds. So stuff like that is certainly fine. It's just not, again, not required. Here's the procedure that you would otherwise follow, but in this case, we've given you all the graphs, so you still have to follow it in some sense. Like you got to open this up, read procedure, and then read what it tells you to do, and then you got to go in and figure out, okay, which graph does this correspond to from the stuff that Mr. Younger posted in Canvas. And that's what you're going to do with all these. So you can see this one is walking distance versus time. So obviously this is about walking, but it's also a distance versus time graph. And it says don't forget to idealize your graphs. You see distance and time. Sometimes these don't come through, even though we're using Word. So feel free to redraw them if they don't look like they do here. Mine seems to be showing everything correctly. Notice also that sometimes they'll have multiple choice type questions or other types of questions like this one right here. It says, in the case of walking away from the detector, the slope or velocity is A, positive or negative. The faster the two trials had a steeper or B gentler slope. So you're supposed to circle these answers. This are you can just box them off, but again, no black. Okay, this is not TypeScript, but still, I don't want black boxes because it's really hard for me to discern a black box that already existed in the graph right. I mean, in the lab write up from a black box that you drew. So all of these questions where they have a right choice and a wrong choice, I'm going to assume the one you marked is the right choice. Okay, so box off the right choice. Don't do something else to the wrong choice because that could be construed as hedging, and you're going to get points taken off for that. Okay. But as you're going along, you do want to answer all these questions, fill out all these multiple choice, put in these lines. You can draw them electronically on here, but I find that really hard. So what might be better is you draw your own graph and then you draw specifically the graph that you wanted to put on here on that. And what you can do is leave the word predicted, but you could completely get rid of this graph, leave the word actual, and completely get rid of this graph. And then you could just substitute a photograph under it, or you could just, substitute a photograph with the word predicted and actual in it appropriately. But that's important when they say predicted versus actual. I need to see both of those, and I need to know which ones are which. So make sure you do that properly. Here's another one. The slope of the graph is constant positive, always positive, but becoming steeper, blah, blah, blah. So all these questions you're supposed to ask, you're supposed to type in answers for describing this motion. You could, for instance, if you wanted to specify exactly what's going on, you could call this, 8 seconds, and you could call this 12 seconds, and then you know that this slowdown or this period at which they walked closer to the detector, took 4 seconds or something like that. Again, those are the what I was saying, where you can put in numbers, but you don't need to. You don't have to. walking versus time, another one, so on and so forth. So you can see how all of these graphs look. And then, as I said, once you're done with all this, you're going to have in this case, it's called a summary, whereas the other lab that we normally do second, but we did first this time, that one had a quiz. This one has a summary. So you might find that the quiz was a little bit more taxing or was a little more taxing than this one, or you might find it the other way around. But the main thing is all of these need to be answered. And as I told you, I will give you model answers for these later on after I grade them. And it's your responsibility to make sure you look back and check to make sure you got the answers right. I occasionally take off some points for getting wrong answers, but it's usually for just not writing an answer at all. I always take off points for you skipping questions, but sometimes getting the answer wrong, I don't necessarily take points off of unless it's just blatantly bad. Other than that, it's more about you trying to learn. So I really want you guys to get these correct by your own, hard work and understanding and working with other people and so on and so forth. Again, if you're just having someone else tell you how to do it, that's not learning. That's just that's just being able to write down the right answer. Now, if your friend or acquaintance is actually helping you understand it, and you ask follow-up questions and stuff like that to try to make sure you understand it, and y'all get somewhere from that, then that's different from cheating. How can I tell? I can't. If you can cheat your way all the way through this, and bad things will come to you later. I'm pretty confident of that, but don't don't think I'm going to catch all my cheaters. Okay, so just use don't punish yourself by cheating. Let's put it that way. All right. So answer all these questions. You can see this one got fouled up because it's on the page break. So if you did do this, you might want to click in here above this four, hit return a couple times so you can put the whole question four down the next page, so on and so forth. All of this stuff should be answered, and you should pay close attention because some of it says one or more, so you're not supposed to just select one answer. So make sure you do all that. Now, in addition to this, you need to understand how am I going to implement this lab, because that lab just told me I had to, open the Logger Pro, I had to turn on the motion sensor, I had to put the motion sensor in a certain position, and I had to grab a pizza box, all sorts of stuff like that. Well, how do you do that because you don't have all that equipment? Well, this motion detector addendum tells you, and it's very, very short. It says this lab will follow the lab book exactly. The only difference is that you will be given the graphs for each section instead of producing them yourself. On procedure 4, stop on page 4 of the lab. Please attempt to predict what the graph will look like before looking at the graph. I know there's a lot of typos in here, and it's really sad that I've copied it literally from the very first year we did it, which was during COVID. And I have yet to decide to change the typo. I think I changed it in one iteration, but I lost it, so I just keep using this one over and over. So, anyways, it really just means that area where I told you to say predict and then actual. It's really that area that you're supposed to do. When you're filling in the graphs on page 12, please use pencil. Remember that all graphs will be either straight lines or smooth curves. Now that's technically true, and that's when we were doing it by paper. We're not doing ours by paper, but if you wanted to, you can certainly use notebook paper to draw the graphs, and then pen or pencil would be appropriate. Pencil would probably be a little easier. That way you can erase mistakes you make. But then you take a photograph of it and then insert the photograph again where it's asked for or where you're told to do it, not just all at the end. I don't. Again, you will lose a butt ton of points for doing it that way. So don't do that. But this is it. This is the whole thing that you got to do in lieu of actually taking the equipment. And that's why I don't feel like it's really necessary to hold your hand while you guys run over the lab. I think I can probably still get us out with, just barely over the normal lecture period of time. Well, I shouldn't say just barely, but some bit over it. But you are welcome, of course, to stay a little longer if we do finish early or whatever. Now that I've gone over this motion detector addendum, I want to go back to the modules and show you the rest. Okay, here we are. So we're back to lab week 4 lab module. I just showed you the addendum. These are those comments I told you about, and as I mentioned in the announcement, one of my students said that's a gift, and they're right. I mean, that's the point of me giving them to you. Is these are comments that I've made on past lab reports that students turn in, and that's what you're supposed to look at when you actually get your graded lab. Is you're supposed to look at the comments that I made, some of which are in the little box off to the right, but other ones are made actually on the document with little bubbles. So you want to make sure you read over those. Well, these are those comments. So if you have the luxury of seeing them a priori, then you can avoid making those mistakes. That being said, I had a lot of students not get, anywhere near a 95 on their first lab because evidently they didn't pay attention to the comments that I gave them. So keep that in mind. It will help you. This is where you're going to turn it in. And as always, you're supposed to turn it in after you take the Word document. And of course, anything that is drawn with a computer or typed with a computer has to be drawn or typed in the document with a font or a line color other than black. Okay, so notice the wording on that is a little bit more expansive than previous wording where I just said anything that was typed. What I'm saying is if you're using boxes, for instance, to box right answers or circles to box right answers, I want those in a color other than black as well so they stand out. Uh, then, like I said, after you use the boxes and implement text and write answers to all the questions that are in there, again, if you see a question mark, you're supposed to put the cursor to the right of the question mark, hit return, 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 and then in the middle of that white space, type in the answer in a font other than black. Again, medium blue, medium green are good choices. But in addition to that, you're also supposed to do in this class, in this particular lab, it's not going to matter too much, but you are supposed to do a sample calc for every calculation that every type of calculation done in the lab. All of those should be put in the lab at the appropriate place, which means either the place where you were told to do it, the place where you were required to do it by just the nature of the lab, or the place where they expected you to do it, but not just all at the end. Okay, so never, there shouldn't be anything at the very end. In reality, when you do lab reports like this, it's right often that would just be where you put reams and reams of data. So the stuff that's important, which reams and reams of data would be for verifying your experiment, but in this case, the stuff's important is the actual results and the stuff you got. So you want to insert all those again once you're finished putting all that stuff in properly, as I explained to you many times before. You want to save the Word document with some part of your name in it, as well as some part of the lab name in it, and then save it again, but this time as a PDF. And the PDF is what you're supposed to turn in. You can see I've already set the date to a week from today at 11:59 p.m. Again, it's supposed to be your labs are supposed to be done by 9:30 in the morning, uh, because that's when your lab meets each week. But when I do it this way, I go ahead and allow everybody to have until midnight. The only reason I really kept it at 9:30 is I don't want you folks skipping class or skipping lab to finish a lab report ever, ever, ever. Okay, I want you to show up to every lab. I want you to show up to every class, and I'd rather you turn in your lab report a little bit late than to skip any of those. So. Down here, like I said, this is actual video of us doing the lab detector, the motion detector lab. So this is where you actually see how the experiment goes. I don't think it's that important to watch this one, for instance, but you can. It's more or less what I'm saying to you right now. Okay, but this one, however, is important. And these are all pictures of the various graphs you're supposed to make. They're what you're supposed to do the analysis on, and those are ones that me and Dr. Wright and Mr. Bruin and some other people made when COVID came. So that's how you're supposed to do this week's lab. Does anybody have any questions on that? All right. Anybody have any other questions? Lecture material, anything like that? Open the chat window, see if I missed anybody. I see Sarah came in and did write her name, as did Dominic. If anybody else came in and didn't write your chat, your first and last name, make sure you do that. Uh, just so I have your name there for attendance. I think it's now a good time for us to get started on vectors in chapter 3. Does anybody have any last minute questions they want to ask about this lab before we go on? Okay, well, remember I have my text messages available and my email available, so if y'all run into any problems after class is over about doing this lab, just, contact me, let me know. I'll see what I can do to help you. If it gets like so bad that, multiple people are asking the same question, then I'll probably post an announcement as opposed to replying to you individually. So keep an eye out for announcements as well as emails. I've been doing nothing but announcements. Hopefully that continues to work. As far as I've been told, my students said that when I do make an announcement, it does come to your email. It's weird because normally whatever email you guys get, I get too, but I don't get those. So that's why I keep saying it like there's some mystery because there's some risk that I'm, doing it and they're not actually going through to you. So I'm a little apprehensive. But I don't see anybody else asking any questions, so let's go ahead and get started. This opening part of chapter 3 is all about adding vectors and vectors specifically, just talking about them. So that's what we're going to do is I'm going to stop sharing the screen now, and I'm going to pull out my iPad, and then I'm going to start sharing that screen so that you guys can follow what I'm talking about on vectors. Okay. So let's go ahead and get started with that. I gotta turn my iPad on. Okay, I'm gonna share screen, advanced, iPhone, iPad. Screen mirroring is not showing up yet. Let me check my Wi-Fi. If I'm not on the same Wi-Fi, it doesn't work. That one's the same Wi-Fi. Let's see what Wi-Fi I'm in this world. I am on the same Wi-Fi, so that should help. So I'm gonna hit share, and now I'm gonna try it again. Ah, there it is. So the big question, what is a vector? Okay. So I've taken time to make up some of this in advance so you won't have to, watch me labor through handwriting, which I didn't want to put in there anyways, but I just don't have the time to type it all. So what is a vector? A vector can be defined as a quantity that has a magnitude and a direction. A vector has other properties about how they change from one coordinate system to another, but that is not yet necessary to understand. So that's a bigger thing that basically vectors are a special case of something we call tensors, and then there's sort of some relatively similar thing called a one form or a form, a differential form that sort of is a complement to these vectors. And all that stuff is really awesome and it's great, but that's not where you need to learn yet. That's something that you might, if you're at a really advanced university or college that had Calc 1, 2, and 3, that might be the kind of thing that you get to cover in Calc 3. But I haven't been to such a college where they've been able to cover that. It's always been more or less a little bit of stuff, almost getting to it, but not quite. But in such a course, you would get something like a little bit of vector calculus, a little bit of differential forms. You'll even find books. I have a book that's basically a Calc 3 book, and it's specifically for differential forms, where you can just use that text in instead of the last, 8 or 9 chapters of your Calc 3 book. That's something interesting. So if you want to study that kind of thing, look it up. I can tell you all sorts of books. One of my favorites, Love, Lock, and Run, Tensors, Differential Forms, and Variational Principles. That's a really great book. But if you haven't finished with Calc 1 and 2 already, it's not going to be much helpful to you. Okay. So, anyways, that's the extra stuff about it. It's not necessary to understand. Right now, you just need to know that a vector is a quantity that has a magnitude and direction in comparison to a scalar, which has just magnitude, and we're going to get to that next. Objects with only magnitude are called scalars, and they do not change just because of a coordinate change. So that's the kind of neat thing about scalars is that though they're sort of not that important in that we find so many things that we can't use scalars to represent, like force, because the force the amount of force you put on something isn't that relevant. For instance, if you had a child or an elderly person leaning against a wall and you pushed with a 50-pound force towards the wall, as long as they're leaning against the wall, nothing's going to happen unless, maybe you pushed on a bad spot and it might make them throw up or something. But if you pushed in a different direction, like parallel to the wall, then you could knock over the elderly person or the kid, and that would be a problem. So that's the kind of thing that makes you think, oh, well, so there's this fundamental idea that some things behave in such a way that their size isn't the only relevant parameter, but the direction that they implement their action is relevant as well. Those quantities we tend to call vectors, and in fact, they get even more complicated. That's why we had to introduce concepts of tensors. So scalars are represented by Greek or Latin letters. I'll be honest with you, we have some of them that are use some Germanic text and all sorts of stuff too. I've used letters from the Hebrew alphabet. Aleph is one of them, and I'm sure I'm horribly mispronouncing that because I've never had any Hebrew training. I've just read books on how to translate Hebrew and stuff of that sort. But yeah, those are all the letters we use because there's just not enough letters in the Greek. I mean, in the English alphabet, which is of course the Latin letters, and there's not enough letters in the Greek alphabet either. So we had to branch out. Uh, Scalars are represented by Greek or Latin letters, and they include pure numbers like 1.0, 2.54, pi, square root of 2, dot, 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 and denominate numbers. That's a technical term that maybe I might be the only person other than mathematicians that know it because I used to teach some really developmental math, and that's the kind of stuff they teach you. Denominate numbers, as you know, for instance, you might talk of a $5 bill versus a $10 bill being different denominations. That's where that word is coming from. So denominate numbers are numbers that have some denomination or some units. So 1 degree Celsius, 2.54 centimeters, pi meters per second, or square root of 2 kilograms. Those are all scalars. Examples of scalars include speed. Notice the first one, speed, starts with the letter S, just like scalar starts with the letter S. I did that on purpose. So speed, mass, time, temperature, volume, those are all quantities that are scalar quantities. Vectors are represented by Greek or Latin letters. Again, the same rules apply there. As sometimes I use, Hebrew alphabet or whatever. If you're doing it in a book, like in print, then those letters will be written as bold print. That's mostly what your textbook author does, for instance. But if you're doing it by hand, bold print's kind of hard to implement, so we do it with some sort of arrow or something. I've seen them with hat symbols on top, but I don't recommend doing that because we use the hat symbols specifically to mean vectors of unit length. So I'm reserving those for that. So don't use a hat symbol. You can use a tilde. I've seen people use a tilde, which is that little curvy line. They've used that over top of it. I've seen them use bars, but we usually use a bar over a number to represent a mean or an average. So don't do that. But examples are velocity. Notice velocity starts with a V, just like vector does. And I mentioned that first, just like I did with speed and scalar first. So velocity. And then I showed you the various arrows I've seen people use. I usually draw a arrow with just one half of the actual arrow points on it, like this one. But I've seen people do it like this, where they actually draw both points and on both ends. I've seen it like this, where they draw just half an arrow, but they put it at both ends. And then I've seen where they draw a whole arrow with both little ends of the vector pointing one way. Uh, a lot of mathematicians I had that wrote it this way, and it just takes a little bit extra work. That's why I usually write this way. Force is another vector quantity. These are semicolons that I'm putting in here, and momentum's another vector quantity. We're going to learn there's a lot more, but that takes us into a realm where you have to think even more about vectors because it becomes something called a field, and that's all more complicated than you need. So, to understand how to work with vectors, it is helpful to think of a specific vector with which you are already familiar, an arrow that represents displacement. So, when I was talking about one-dimensional motion, I mentioned to you guys to imagine an arrow that points from where you were to where you ended up. And that is a displacement vector. That quantity is called displacement, and the fact that it can be treated like an arrow because the arrow has a length which represents a magnitude, which could be proportional to a magnitude in some sense, and it has a direction. It has a end with no arrow on it, and that's the tail end, and then it has an end with a arrowhead on it, and that's the head end, and therefore it specifies a very specific direction. So the displacement vector for any motion is an arrow that starts from the same point at which the motion started, and that points to the final position that ended the motion. So notice I said a vector for any motion. So for a specific chunk of motion, like standing on the edge of your front porch, walking out to the sidewalk, that's one piece of motion. And I represent it as if you started at point A, as you can see in the example, the figure down at the bottom, or right below the word example. You can see it's as if we started at point A, and then that dashed line represents the motion from point A to point B. So, and not only that, I put the letters in alphabetical order so that you'd know A came before B, so that A was the beginning position and B was the final position. So, to represent that with a vector or an arrow, we draw a vector from point A to point B, which is what I did in the second diagram. So, it says the dashed line represents motion one. The red arrow is the displacement for motion one, and therefore I labeled it D1 because D is the first letter of the word displacement, and one with a subscript as a subscript is basically to represent that, hey, this is the displacement vector for motion one. Then I went a little further to give you another example. Imagine that once you got to B, you then walked another distance, but this time you walked perpendicular to your last direction, because before you walked from left to right, now you're walking from bottom to top. Okay, that could be you walked due east in D1 and you walked due north in what's going to be called D2. So you can see in the third diagram, which is the one on the far left at the bottom, we have a dashed line going from point B, the same point B we had in the previous two diagrams, but a dashed line going from there to C. So that's what I called motion two, just by analogy of what we did in the first diagram. And then the second diagram in the bottom, in the middle, that one shows me actually drawing a arrow from B to C, and then I labeled that arrow D2 because that is displacement 2. Okay. And the whole reason I did this was because I wanted you to see how the displacement is very different from, for instance, the distance traveled. If you look at the length of D1, it is clearly the distance traveled. If you look at the length of D2, it is clearly the distance traveled. But if you look at this bigger displacement, so if you treated the motion for the sake of making a displacement vector as your initial position A to your final position C, then that can be considered motion as well. The details of what goes into the motion, whether you make turns and all that stuff, doesn't really matter. All you need for average velocity, for instance, is the displacement. And the displacement always starts at your initial point and then ends at your final point. So in this diagram, we started at point A, which was right next to the porch. We went to B, and then we hung a left, and we went to point C, and that's when we stopped. So our displacement from A to C is our total displacement, or you might just call it displacement A to C. So I wrote that as a displacement vector D, A arrow C, which means A to C. I could have just wrote that as AC, but I wanted to be clear exactly what I was talking about. So I said A to C with a little arrow. Now, we define this quantity, the displacement from A to C, as the sum of the two motions. So we have a displacement D1 for motion 1. We have a displacement vector for D2 for motion 2. Therefore, the total displacement of 1 and 2, motions 1 and 2 total, is the displacement vector over the entire motion from A to C, and therefore it's that green vector that I drew from A directly to C. Notice the displacement vector doesn't have any real familiarity or commonness with the actual path of travel. The only points at which it even touches the actual travel was the very beginning point and the very final point. That's perfectly normal. Okay. So now you can say, hey, this looks like a triangle. And in fact, if I am certain that the D1 was due east and the D2 was due north, then those two are perpendicular to each other. And I know exactly how to compute the magnitude of the vector DAC, which happens to be, like I said, the sum of vector D1 and vector D2. Anybody know how to come up with the magnitude if I were to give you, for instance, the distances of D1 and D2? I'm asking anyone a question. Can you tell me how to find the length of the green vector if you were
You use
given the
Pythagorean
length
theorem,
of
correct?
That's correct. Yes, since those are since that's supposed to be a right angle, then that makes a something that is a right triangle. And according to the Pythagorean theorem, the sum of the squares of the legs is equal to the square of the hypotenuse, and the actual resultant. That's another word for the sum of two vectors is resultant. Resultant. That is the square root of the sum of the squares. Okay. How about direction? If that truly was north, going from B to C, and A to B was east, can anybody tell me how you might figure out what direction vector DAC is?
The tangent function.
Exactly. So if you took the tangent, which is opposite over adjacent, if you're talking about this angle, let me show you specifically exactly which angle I'm talking about here. Uh, I'll use this pointer. So if we're talking about this angle right here, then that angle touches this side, and therefore this side, which is not the hypotenuse, has to be the adjacent. Okay. And this side, which is also not the hypotenuse, but it's not touching the angle, so that's the opposite. Now, if you look and notice that would be where we actually put our right angle symbol to show this is a right triangle, it looks like an arrowhead. See how it looks like an arrowhead? And that arrowhead automatically points to the hypotenuse. So that's how you can tell on a right triangle which one the hypotenuse is you imagine the right triangle symbol being drawn and you imagine that being the head of an arrow and then lo and behold it's pointing right at the hypotenuse. Okay? So as I said and as you correctly pointed out, the tangent of let's call this angle theta, the tangent of theta is equal to opposite, which would be the magnitude of d2 over the hypotenuse, which would be the magnitude of d1. Okay. Not only that, the magnitude of DAC, which we could write this way, that's a way we typically write magnitude of a vector is we draw the vector symbol and then we put absolute value bars on it. A lot of people don't like that, so sometimes in math class they'll put double absolute value bars and sometimes they'll even put little things like that on it. I don't see any point in that either, but either one of those symbols is fine. But to be honest with you, the best symbols in my estimation for the magnitude is this highly efficient one, which is you just take the arrow off of the top, like I did here and here. So if you just take the name of the letter that represents a vector or the symbol that represents a vector and you just erase the arrow off the top, then or whatever indicator you're using, then you're specifying the magnitude. And as we said in this case, the magnitude is given by the Pythagorean theorem, and we don't have negative magnitudes of vectors. Okay. We can have negative components, but we don't have negative magnitudes. So that means we're forced to take the positive square root of d1 squared plus d2 squared. So that's how you do it if you just so happen to have two vectors that are perpendicular to each other. As you could tell, if you had many vectors instead of just the two, like displacement one and displacement two, things could get a little different because there's no Pythagorean theorem for, a polygon, right? But there is a way I can help you with that. Anybody have any questions so far? All right, so this displacement is going to be our continuing model of how to actually add vectors. So I'm going to move on to the next page. Uh, b- 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 that's weird. Oh, I see what happened. Yeah, so I had set this up to be nice and neat where you can see this part and then you'd see that part. This is probably worthwhile for you to see now. It's just I came to the slide earlier because I hadn't erased this one evidently, but I did copy it all to make sure I could erase it, and then I just went back and forgot evidently. But anyways, so if you look at the time progression, you can see what happened. First off, we imagined a trip. We walked from A to B. And then I explained to you that the displacement with that would be the red arrow that goes from point A to point B. And then I said, let's up the ante. Let's consider another displacement from B to C. Now I represent that displacement as the vector D2. You can see it there. And then I say, well, let's now integrate the idea that the displacement of multiple trips is just the sum of the displacements of the individual trips. So vectorially speaking, that is what we found out. And in this page, I should go ahead and write down that this was the angle theta, and we found that tangent theta was equal to D2 over D1, opposite over adjacent, and the magnitude of DAC was equal to the magnitude of DAC was equal to the positive square root of D1 squared plus D2 squared, like that. So that's basically what we had, and this was all just supposed to be erased, except for that first symbol. So now you can see what I really intended to do, but I screwed it up. So, anyways, anybody have any questions on that? It looks like y'all are following pretty well. Oh, got another student that, oh, they were here already, so I think she might have been bumped out by accident. All right, so working with that model, you can see, for instance, in a more general scenario, let's imagine a coordinate system. Let's specifically imagine a coordinate system like this. This would be my x-axis. This would be my y-axis. Now, we could imagine, just like we did before, a trip to the right, or which would be east. That's the other thing that we do here is when we make such a coordinate system, we understand the y-axis to be due north, which also happens to be a compass heading of 0 degrees. Okay. That also means that this is due east and this is 90 degrees compass heading. And I keep having to put that specifically because you guys know from your study of trigonometry and pre-calc that there's a very specific angle that we measure counterclockwise from the positive x-axis. That's a whole different angle. So if I just wrote the angle there, you might confuse it for that one. I'll get to that in a second. This direction down here is south, and that corresponds to a compass heading of 180 degrees. And this corresponds to west, and that corresponds to a compass reading of 270 degrees, like that. And of course, north also happens to be 360 degrees, so that's acceptable as well. Now, I'm going to show you yet another way in a second, but now we can say, what about now if I take another trip due north, and this time I'm going to go this distance? Okay. So on the scale that we're using, let's say assume is 10 newtons. and assume this distance. Again, I'm trying to draw just the thickness of one of the graph paper squares, if you will. This is also 10 newtons. Okay, so that means this blue vector here has a magnitude of 30 newtons, and this purple vector here has a magnitude of 40 newtons. And I could actually say that's 40.0 or whatever, but we're not worried about sig figs right now. So as we just learned, the displacement one, which was the 30 newtons east, and then displacement two, which was 40 newtons north, the sum of those two is in fact a vector that goes from the origin to that last spot. And of course, we can use our knowledge of trigonometry and work it out, but we suspect you guys already know a lot of stuff about this one. So just to check our work, the tangent theta is supposed to equal 40 newtons divided by 30 newtons. And of course, that means theta equals the tangent inverse of 4 over 3. In other words, I reduced everything else. And I think you're going to recognize that angle when you take your trig function and say shift tan 4 divided by 3 in parentheses. That gives me 53.13, because this is the famous 3-4-5 triangle. And the angles are, of course, 53.13 uh, and 36.87. So this angle up here, for instance, let's call that phi. Phi equals 90 minus 53.13, and therefore is equal to 36.87 degrees. Okay. Now, the other thing we claimed was we could use the Pythagorean theorem to find out what the magnitude of that vector is, and we can. So we're going to say, actually, I'll put that in the same color as we used here. Let's call this R, and I'm using that for a very specific reason. The resultant is equal to the R vector, and the magnitude of the resultant is equal to the square root of 30.00. I'm pretending now like we had 4 sig figs just because I can, and I like it better. That's going to be squared as well, and I take the square root, and I think you will all figure out that that is the wonderful number 50.00 newtons. So that's a way that we can work out the vector sum of two vectors when they happen to be perpendicular. But what happens when they're not perpendicular? So let's try this time. Oops, that's really bad. Close enough. So here's our x-axis. Here's our y-axis. And by the way, you can use any coordinates you want. You can make the x-axis pointing up and the y-axis pointing to the right. That's fine. That's one of the fundamental laws of physics. Special relativity says the laws of physics are the same for all inertial observers, and then general relativity says the laws of physics are the same for all observers. And that's basically trying to say, hey, no matter what coordinate system you're using, and whether even if that coordinate system is moving relative to the actual object, you're still going to get the same laws of physics. So you're still going to get the same laws of physics here, no matter what coordinate system you use. You just got to be careful about not using left-handed coordinate systems, which, as long as you're in 2 dimensions, that's not going to happen. It's only when you add the third dimension, which in this case, according to the right-hand rule, notice how I'm holding my right hand. This index finger would represent the x-axis, which is pointing to the right. This middle finger, which is representing the y-axis, has to point up, and then you see my thumb is pointing out of the screen. So what that tells you is if you wanted to draw a z-axis, you would have no choice but to draw the z-axis coming out of the page to us. So just keep that in mind. Long as you always draw a right-handed coordinate system, you'll be fine. And if you're only using X and Y, you don't even have to care about the direction of the Z-axis. But if you do something like a cross product, which gives you a perpendicular vector, you'll automatically fall into the third dimension. So just keep that in mind. So now let's imagine something a little more sinister and complex. What if we did a little displacement D1 and then another displacement D2? The actual resultant of those two would be this one that I call R1. But what if yet instead of just taking two trips, what if I took a third trip from that second position, the end of D2? What if I took this trip and I'd call that D3? And then I took this trip and I'd call that D4. And then I took this trip and I call that D5. Well, that's the beauty of the displacement, the way I defined it. Each of these vectors are individual motions, but they're short little straight line motions, probably, right? Then the result of the total motion is always from the very beginning spot, which is the origin, to the very final spot, which is the end of D5. So you can write the displacement vector as this resultant R. Okay. And maybe I'll call that R sub t, meaning total. So that's what the vector addition is for all of them. Okay, no matter how many you put, if you just keep putting them tail to head to tail, head to tail, head to tail, like I did here, notice I'm saying head of this vector to the tail of this vector, and then the head of this vector is on the tail of this vector, and then that head of this vector is on the tail of this vector. And then the tail of this vector is on the head of this vector. So now I have this as the final one. So that's our final result. If you think about this, you can look at it and say, it's almost like I went a little bit of a distance to the right and then I went a huge difference to the left, a distance to the left. And it's also like I did a huge distance up vertically. And that is really you starting to think in terms of components when you get that. You could say, all right, well, how many times or how far did I go east? And you'd say, okay, well, I can look at that little vector D2 here. I can look at that little vector D2 here. And I'm drawing in red, I know. But I can imagine that little vector D2 as an east part, and then I could imagine that little vector D2 as having a north part. And again, that would have some angle theta in there. And come to find out, what we mean by this is, for instance, if you had a vector like this, then you could sort of imagine this thing down here as a shadow. Notice if you imagine the sun coming straight down and you imagine this green crooked vector, if you imagine that like a piece of plywood, you would see that all of this would be dark because the sun's shining straight down, and because of that, it's casting a shadow. Well, the shadow of the vector D2, which is what this represents, is on the x-axis. That's the x component. So what we'd call this is d2 sub x. And since it has an arrow on it, we're actually would call that the vector d2x. And the magnitude of that would have to be positive no matter what. But we can still give it a sign to indicate that it points to the right or to the left. That's how we deal with a one-dimensional vector. Similarly, we could imagine this vector right here as being D2Y. And that's sort of like the shadow that a horizontal laser beam would cast on a vertical wall as a result of the vector D2. So, where I'm introducing new terminology here, d2x and d2y are called the component vectors. Or I actually, since I left the vector symbol off of it, I'll just say are called the magnitudes of the x component and whoa, I wrote any instead of and whoa, now I wrote add. I don't know what happened there. And y component respectively. In other words, the one that has the x on it is obviously the x component, and the one that has the y on it is obviously the y component. And from straight trig, you know, for instance, if this angle really was theta, then if we knew that theta and we knew the magnitude of d2, then we could readily figure out the component dx, d2x, and the component d2y. So, for instance, assume d2 is equal to, let's say, 3.0 meters, and theta is 30.0 degrees. Okay. Then we could just slowly write down the components or the trig function. Specifically, when you have a vector in place and you've got an angle between that vector and the nearest axis. In this case, I happen to choose the x-axis, but I could have chose the y-axis. That's fine as well. The trig functions come out a little differently, but the answers still come out the same. The x component always will be the x component. The y component will always be the y component. So in order for me to go ahead and compute the x component, what I first want to do is tell you guys to first write out your trig functions. So sine theta, I used the mnemonic some old horse came hopping through our alley. Notice the redneck phrase there that I like to use. Some old horse came a hopping. Okay, so that we can get cosine equals adjacent over hypotenuse through our alley because tangents equal to opposite over adjacent, and some old horses sine equals opposite over hypotenuse. You can also use so ka toa. That's what most people I run into uses. But in this case, we're going to say sine, and I am doing third sine of theta, but specifically, I just called the theta 30 degrees. So the sine of 30 is supposed to be opposite over hypotenuse. The opposite side, remember our trick, this angle is touching this side, so this one's the adjacent because it's not the hypotenuse. We know it's not the hypotenuse because this arrow points to that one, which is the hypotenuse. So we see that the opposite is d2y. So I'm just going to put d2y over d2 because the hypotenuse is the magnitude of the vector itself. And then we're going to write cosine theta, which is cosine 30 degrees, is equal to adjacent over hypotenuse. So that's d2x over d2. Now, doing it this way is absolutely right, but you've always got to look and say, well, which direction does dx point? Does it point the same direction as positive x? Because if it does, then it's supposed to be represented by a positive x component. But if it points in the opposite direction of x, it should be classified as a negative component. Same thing with the y component. If it points up, that's normally what we consider the positive direction. And if it points down, that's going to be the negative direction. So you have to force that sign in by always using the angle between the vector and the nearest axis. You're going to have to use the sign convention that your coordinate system allows, as opposed to letting the trig function spit out numbers and signs. You don't want to use trig functions that way. There's a lot of problems that come in, especially when you start using inverse trig functions, and when you're messing around in the third quadrant, for instance, there's a lot of problems because the third quadrant has both the x and the y negative, and you can see obviously if you divide the negative by a negative, you get a positive. So it can be a little bit redundant unless you're using computer programming where they have specific coordinate dependent trig functions, and then it works a little better. But the main thing here is to see that d2y from this one is clearly equal to d2 times the sine of 30 degrees, and we just said d2 was 3 meters, so I'm going to say 3 times sine 30, and that gives me 3 over 2, which is 1.5. And the cosine gives me the ability to sign for d2x, or to solve for d2x, and that's d2 times the cosine of 30.0 degrees. And of course, that's 3 times cosine 30. You got to make sure your calculator's in degree mode to do this. And this one gives me 2.5. Actually, I should call that 2.60, even though I really only have two sig figs to go with. And that's meters as well because the other one was in meters. And to make this consistent, I'll go ahead and write a 0 with a line under it and an M there too. So that's how you find components. If you chose to use this angle right here, then you would get different trig functions. You'd get the sine of phi is equal to opposite, which would be this guy, which you can see is d2x over hypotenuse would be d2. And then the cosine of phi would equal the adjacent over hypotenuse. So that's d2y over d2. If you actually do that computation, you'll see that you get exactly the same answers I did when I used the angle theta. And that's sort of the point. Notice we used sine this time to find the x component, whereas we used cosine last time to find the x component. That's the reason they're called sine versus cosine. The sine of an angle is equal to the cosine of the uh, corresponding angle, or the other complementary angle. That's the word I was going for. So that's why they use the CO in cosine. The sine of theta is the cosine of the complementary angle to theta, and the complementary angle means the angle that you get when you subtract the original angle from 90. So if I subtracted 30 from 90, I'd be doing 60. So if I put sine 60 and then multiplied that by 3, you would get, in fact, 2.60. And if I did cosine 60 and multiply that by 3, you would in fact get 1.50. Any questions on that? All right, now that we have that, you can start to think in terms of adding multiple vectors as having some way of doing it. So let's imagine again a coordinate system of our making. And I will imagine several vectors. There's going to be a vector here. And then that vector, of course, is going to have a positive x component. And the reason it's positive is because by drawing that arrow, I am trying to indicate that this is the positive x-axis. And by drawing this arrow, I'm trying to indicate that that is the positive y-axis. So I would have that, and then I'd have this for the y component. Then the next vector I might add to it would be maybe this one. And this one actually has a positive y component, or positive x component, and a positive y component. Now the next one I draw might be here. And now you can see this one has a negative x component, but it also has a negative y component. We could go from here to here, and then you'd see that one has a positive y component, but a negative x component. And then one more vector looks vertical. So in fact, it has only a y component because it's vertical. The resultant of all these is that vector right there. So by putting the vectors head to tail, head to tail, head to tail, head to tail, you just draw a vector from the tail of the first vector to the head of the last. That is how you add vectors graphically. So to add vectors graphically, place all of the vectors actually in any order. So you place all the vectors in head to tail positioning, and the resultant is the vector from the tail of the first to the head of the last. Okay? So that's the big wording. If you have your vectors and you put them all head to tail, head to tail, head to tail, and in any order, like the first vector could be A, the second vector could be B, the third vector could be C, the fourth be D. But then you could draw first off from the origin, you could draw vector at C, and then at the head of that vector you could put the tail of vector B, and then at the head of that vector you could put the tail of vector D, and then at the head of that vector you could put the tail of vector A. It doesn't matter because there's a rule that says basically A plus B plus C is equal to A plus B plus C. That means, for instance, I can add the first two first and then add it to the third, which is what the right hand side says, whereas the left hand says I can add the second and the third vector together to get, and then add to that the first vector. That's just telling me that it doesn't matter which two I take piecewise, but I could, in principle, add vectors piecewise, taking two at a time, get a result, then take another one with that, get another result, then take another one with that, get another result, and that would all work out. But not only that, it also turns out that A plus B is equal to B plus A. So between those two properties, you know that you can put them in any order you want, as well as uh, you can also add two of them at a time instead of just taking all of them at once. So I could take the first two vectors, find the resultant. The first two vectors were not at perpendicular to each other, so it's not like it makes it any easier. But in principle, I could add them, and then someone says, "Okay, now add the third vector." Okay, now I just take that new vector that I got by adding the first two, and just say I don't have to think about the first two anymore. I can just add that one. Okay. So that's how you add vectors graphically when they're head to tail. Now I'm going to show you what happens if they're tail to tail, because that's another way people often put vectors together. So there's my x and there's my y. And what we can do is we can say, imagine this vector is A, and let's imagine this vector is B. Those two vectors are tail to tail. Okay. The way you can add those graphically is a little bit different than the way you add them when they're head to tail. But what you can do is you realize that in our definition of the vector, all we said was that the vector had to have a magnitude and direction. Since that seems to be the important data regarding the vector, as long as you don't stretch the vector or compress the vector, in other words, change its magnitude, and as long as you don't rotate the vector, meaning change its direction, then you're allowed to do whatever you want with the vectors. Okay. Now, this will be different when we talk about vector fields and stuff later, but we don't need to know about that right now. You won't need to know about that until 242. But right now, as long as you're just dealing with vectors like these vectors are meant to be in space. They're not, assigned a point in space or anything like that. They're just in space and you're allowed to move them freely. So the first thing I'm going to do is imagine as if vector A if we looked really close at the tail of vector A, it would look like this, and we'd see vector B going up like that. Okay. So what I'm going to do is imagine that little hole is like something that keeps the vector connected to the purple vector, but lets the purple vector act as an axis. So I'm going to slide vector 2 right along vector B. And when I do that, I'm going to get, actually, it should go right about there. Oops, I should have drawn that red. Hold on a second. Okay, so that vector should be exactly parallel and exactly the same length as A. So it's just a redrawing of A. Now you can do the same thing with B, only this time you now pretend that B vector has a ring on it and A vector goes this way. Now we're going to slide the B vector along the A vector. And when we do that, we're going to get this right here. So now you can see that these two versions show A and B in head to tail formation. Of course, so do these two vectors. So either one of those can be used to figure out our answer, but we know that when you have vectors head to tail, you draw a vector from the tail of the first to the head of the last. In the bottom set, these two, the tail of the first is there and the head of the last is there. So the resultant should be this vector right here, R. Okay. Now, if you forget about those two, you could also use the top two. And you see the tail of the first is right here, and the head of the last is right here. So again, you're going to draw a vector from here to here. So either way, you get it. Now you know how to add two vectors tail to tail. And here's our result. To add vectors, and this is technically two vectors that are tail to tail, you complete the parallelogram and draw the resultant from the common tail to the opposite corner. So you draw it from the tail, the common tail, which is obviously right here, to the opposite corner of the parallelogram. Any questions on that? So I've now shown you how to find components of vectors. I've at least told you how, and I've told you how to add vectors graphically, both head to tail, and a string of head to tail. Notice you don't want to, you can still string a bunch of vectors tail to tail, so you wouldn't necessarily have to just take two. You could, in principle, add any number of vectors all tail to tail, but what you do to do that is you can take any of the first two that you want to make any two the first two, add them like this graphically, then take that one and add it with another one, again graphically, and then take the resultant of that one, add it to another one, and keep doing that until you've added all of them. Once you're done, you will have the resultant, which is the sum of all the vectors. Okay, so in this case, we had our total. In the top case, we had our total was, A. Well, let me write it this way. I'll say this is A, and this is B, and this is C, and this is D, and this is E. So our total is equal to A plus B plus C plus D plus E. But again, any order would be fine, and any two that you take at a time would be fine. What I want to do now is argue a way to figure out what the difference of two vectors is. And to make sense of that, I'm going to give you another rule that we learned from algebra. So we learned A minus B is really defined to be A plus the additive inverse or the opposite of B. That's what we learned. All of this comes from the fact that the idea of an algebra is a thing, and those weird properties that we learned initially, like the distributive property, uh, the commutative property, the stuff like that, as well as the definition of subtraction. All of those things that you learned early on in algebra are the key characteristics of what we call an algebra, and vectors make an algebra called vector algebra. So that's why it's coming up again, because that's sort of a fundamental definition of something that we found useful to science and everything. So now that we have that, we can put this in the language of vectors and say that vector A minus vector B is equal to vector A plus the opposite, the additive inverse of vector B. So we got to explain to you what the additive inverse of vector B is. Well, if you wanted to think about vector A and vector B as if they're going to be subtracted, what if vector A and vector B were both B and negative B? In other words, what if I wanted to subtract B from B? Anybody have any idea what answer I should get if I do B minus B?
Zero.
Exactly. So That's going to be the zero vector, and a zero vector has no magnitude or direction. It's just a point, basically. And this allows us better to figure out what b and negative b are. If I wanted one vector to be completely undone by another vector, what I'm imagining is my vector initially might be this one, and I want to add to it something that gives me nothing. Well, the only thing I could add to that to give me nothing is a vector exactly the same length, but in the opposite direction. So if we think about it that way, then the purple vector would be b, and the red vector would be negative b. And now we have an idea of what the opposite of a vector is. It's taking the vector and putting a negative sign in it, but it means flipping the direction. In fact, opposite of b is negative 1 times b. So we've just figured out something about multiplying vectors by scalars. It turns out if we multiply it by a scalar whose magnitude is 1, we're not going to change the length at all. But if we multiply it by a negative 1, then we're still not going to change the length, but we're definitely going to change the direction. So that's our first rule of multiplying scalars by vectors is if you multiply by a negative, you're going to reverse the direction. If you multiply by a positive, you're not going to affect the direction at all. Okay? So that means, for instance, if this is vector C, then this is vector 2C, and this is vector negative C, and this would be vector negative 3C. Okay? So you can see that they're all supposed to be related. In other words, if you multiply by a positive number, you don't change the magnitude at all, or excuse me, you don't change the direction at all, but you do change the magnitude. And specifically, if you multiply by a number bigger than 1, you're making the vector get bigger. If you multiply a number that's smaller than 1, you're making it get smaller. So for instance, we'd say that this vector is 1/2 C. So now we've been able to start off with an idea of adding, subtracting vectors, and that introduced us to something called the opposite of a vector. And we were able to convince ourselves that the opposite of a vector is a vector that has the same magnitude but points in the opposite direction. And we realized that since they were calling that negative b, and we remembered from algebra that negative b means take b and multiply it by negative 1, we were able to figure out what multiplication by a vector means. I think I didn't give you all the details, but I would suspect this seems like the most reasonable definition of scalar multiplication. For instance, if you think in terms of a displacement, if you said, okay, I walked from A to B due east, then someone told you, okay, well, what's twice the displacement vector there? You'd probably think, oh, well, I have to walk twice as far. And if you thought about changing directions, you say, well, what would be a reasonable direction? Well, the reasonable change in direction would either be completely 180 or nothing. And 180 we've reserved for negative numbers, so I would assume that we're not going to do any because any angle other than exactly the opposite, there's no real reason why you would focus on that angle as opposed to any other angle. So the only one that makes any sense is when you multiply a vector by a scalar, either it's not going to change direction at all or it's going to flip direction completely. I just established that when you multiplied by negative 1, it flipped direction completely. So now the other aspect is if it's a positive, you're not going to change the direction at all. Okay. So now let me show you how you add or excuse me, how you subtract one vector from another when they're in head to tail position. So here's our coordinate system. And let's say we have this vector A, And then we have this vector B. And I want to know what is A minus B, which, as I told you, is defined to be A plus the opposite of B. So, first thing we're going to do is we're going to turn around B, and this represents negative B. But now I've got the two vectors head to head. What does that mean? Well, that just reminds us that, hey, this isn't very useful. I haven't learned anything to do about this. So, is there some way I can move this vector or one of these vectors so that they're then head to tail or tail to tail? Because my job now is to add this green one and the red one because that's the definition of subtraction. So, if we imagine the green one sliding horizontally, then what you get is the green one going right here. Oh, might help if I use the right marker. The green one is now going to be, notice it went over to the right one square and it went up three squares. So I'm going to try to do the same thing over to the right. Oops, I wrote the arrow on the wrong end. So this is negative b put over here. Now you can see that the vector negative b and a are head to tail, and we know that the sum of two vectors head to tail is just from the tail of the first to the head of the last. So we can get that the resultant vector is just that quantity. Now, it might help you to go ahead and imagine doing the same thing with the red vector that we did with the purple vector. And then you'd see that, oh, A plus negative B, if I added them tail to tail, I would get exactly the same result as I got here for R. Oops, that was supposed to be in blue. Now, it might have been smart for me to call this D or something for difference, but the main thing is because you have to still do an addition when you're subtracting vectors, uh, it's perfectly reasonable to sometimes refer to that as R as a resultant, even though it's not really a resultant. Resultant is supposed to be the sum of vectors. And in this case, I just called it R. Okay? So everybody sees that to subtract a vector B from the vector A, in other words, A minus B, you reverse the direction of B and then add them. And I'm just saying A and negative B to remind you that reversing the direction of B makes negative B. Now, what I just started with was two vectors that were head to tail, and you saw it was kind of messy subtracting when they're head to tail. Whereas earlier, when we added vectors, head to tail was really easy, but tail to tail was difficult. So here we see when I had two vectors head to tail, like I did here, okay, I had to complete the parallelogram and then draw this vector. So that's kind of a pain. What if instead I was given two vectors that were tail to tail and asked to subtract them? So here's my x-axis, here's my y-axis again. Now I'm going to take this vector A, which went up 1 and to the right by 4. So up 1 and to the right by 4. There's A. And B, remember I went up, or I went to the right one and up three. So to the right one and up three, that is B. Okay. Negative B, on the other hand, is this guy. And now you see that A and B are head to tail, and of course that means the resultant is from here to here. And this is when they are tail to tail. Okay, everybody follow that? It's very important, as you hopefully you might have already seen it in your practice tests, but when you go to add vectors graphically, there will actually be questions on your test where you're going to have to do this, where I'll just give you two vectors drawn on the paper, and your job is to draw the representative vector for the sum of the two, or for the uh, a minus b, or for b minus a, or whatever. So you've got to be able to do this. This is not an optional skill. And not only that, if you actually have access to like AutoCAD or one of those type things, if you have that type of software that allows you to make vectors in very specific or arrows in very specific directions and very specific lengths, like you can in AutoCAD, you can use the head to tail method or the tail to tail method, or multiple head to tail methods, and it will, by using AutoCAD, you can draw the resultant vector from that drawing and measure its properties, and they'll give you exactly the right answers. That's if you do it correctly in AutoCAD or something like AutoCAD, you'll get exactly the right answers. So you'll be able to actually compute this and try it on your own graphically. So, anybody have any questions on that? Let me write down the rule for multiplication by a scalar. I'll just call it scalar multiplication. Okay, so scalar multiplication. If you multiply a vector by any positive scalar, you will only change its magnitude unless the scalar is 1.000 for infinity. If you multiply a vector by a negative scalar, the vector will have its direction reversed. If the scalar has a magnitude greater than 1, the vector will be elongated. If less than 1, it will be shortened. In fact, the magnitude changes by exactly the right factor. So if you multiply a vector by 2, then the new magnitude will be 2 times as big as the old magnitude. If you multiply a vector by 2.78, then the new vector 2.78a will be 2.78 times longer than a. If it happens to be a negative, it's also going to have 180 degrees added to its direction. Remember, reversing just means add 180. You could also let it mean subtract 180. That would be fine as well. But that's the way you find a opposite vector or an additive inverse vector is by rotating the vector 180 degrees from the original vector direction. Any questions on that? Okay, so now let me start with the world's greatest vector problem. Now, what we're going to do here is we're going to attempt to add vectors, specifically according to some vectors that I drew earlier. That's really not good. Let's see if I can draw this a little better. Okay. I used the cleanup tool to write it a little better. So this is going to be my x-axis and this will be my y-axis. Remember, this also corresponds to north and 0 degrees compass heading. And this is east and 90 degrees compass heading. Okay, so the first vector I'm going to do, I'm going to write them over here. Let's say, I did not mean to do that. Let's say A, and this is some ways I could write it, is 14.14 uh, newtons at 45.00 degrees. That's one way we can specify it. And what we mean by that is that its angle is in the traditional position because all I said was at, and then I gave you an angle. So when you do that, that says to the person that's reading it that, hey, uh, I want the angle measured to be exactly 45 degrees, and it should rotate counterclockwise since it's positive from the positive x-axis. If it was a negative angle, like at negative 45 degrees, then you would choose to make it uh, as a rotation counterclockwise from the positive x-axis. So I'm going to lay a protractor right here, and what I have is this protractor has a little hole right here, and you'll notice that that hole has two little lines, one going out to the right, one going out to the left, and they point exactly to the 0 degree mark on this side and the 0/180 degree mark on this side. Both sides are marked 0 and 180, but the main thing is that circle is the middle of the circle. There are some protractors where the bottom edge is supposed to be, so you need to check that with your protractor before before you do it. But what I'm going to do is I'm going to draw this vector A at the origin by putting the circle at the origin, and then I'm going to lay this line that says 0 degrees all across here. I'm going to lie that on the x-axis in the positive direction, and I have done that. Now I'm going to mark on this page exactly where 45 degrees is, and it may or may not be the right length out. It almost never is. But now I have a red dot that represents the direction that I want this vector to point. And now I can use a scale to actually draw it 14.14 meters, or newtons in this case. But what I'm going to do is I'm going to use my ruler, and I'm drawing it supposedly a 45-degree angle right to there. Now that's markedly larger than I probably want. I'm going to use a scale on here, and I'm going to say that 14.14 is about equal to, I'm using centimeters here, is about equal to 1.4, which would be right there. That allows me to drop this all the way to that spot. And now I can just say that's vector A. Now, the next step to adding vectors is I need to draw another coordinate system at the tip of that, because I want to be able to draw these vectors head to tail. So in order to do that, I'm putting down another straight edge to try to be as precise as possible. Actually, I'll just do it this way and hope the locking in does a good enough job. So there's my new x-axis, and there's my new y-axis. Now, right there, I want to draw the next vector, and the next vector is vector B. And vector B, sorry about that. Since I left it on that neat drawing, it's trying to change my letters into something geometric. This one's going to be 20.00 newtons at, now it says 30 degrees south of east. I'm just going to write that as SOE, south of east. But remember that terminology, because south of east means you're supposed to point it downward and to the right a little bit. So in this case, I'm going to have the angle point downward like that, because this is now my x-axis and this is now my y-axis. Okay. But in this case, it's supposed to be 30 degrees, so I'm going to use my protractor again to point out 30 degrees. This looks like I got a good estimate, and this should be 30 degrees right here. So now I'm going to take the blue and draw another vector at the tail of this one. I mean, at the head of this one. So that is the actual vector. But in this case, since 14.14 was approximately equal to, this is the scale I'm using. Oh, that was aggravating. That's really aggravating. 1.4 centimeters equals 14 newtons roughly. Obviously, I wanted 14.14. That's not going to be precise enough for me, or my meter stick on the computer is not going to be precise enough for me to get even maybe even one decimal place. But in this case, that's the same thing as saying 20, and that wasn't centimeters. It's supposed to be, yeah. That should mean that 2.0 centimeters is equal to 20.00 newtons. So now I'm going to make sure I cut this off at 2 centimeters. And to do that, I need to, I'm putting a ruler up here. and 2 centimeter mark is right there. So now I'm going to erase all of this. And technically I don't want any of that there either, so I'm going to try to erase all this. So there's my vector B right there. Now again, I need to draw another coordinate axis at the head of that vector. And in this case, it's probably going to be helpful to draw the all the coordinates, not just the positive x and y. This one's going to be vector C. Vector C is supposed to be equal to 25.0 newtons at 53.1 degrees, and this is west of north. So I need to draw an angle 53.1 degrees, basically pointing this way, because that's west of north. So I'm going to draw a vector that is 30 degrees from there. In order to do that, I'm going to put the zero right on, or this, I'm going to put the center of the protractor right at the crosshairs where the blue vector meets the center of the origin. And now I'm going to mark off 53.1 degrees, which would be right about here. I'll draw that in black so it stands out a little better, but that's the dot that I'm going for. And this one's supposed to be 25 newtons, so that's going to be 2.5 centimeters. But you can see roughly this should look like a vector from here. Oops, undo that a little bit, got off track. So that's roughly the right direction. Now I need to cut it down to 2.5 centimeters, which means we should go to right about, it's so hard to see this, right about there. Okay, so that's vector C. And now vector D is going to be, that's going to be 40.0 newtons. And this one is at compass heading of 240. 240 degrees. Now I know 180 is due south, and then I need 60 degrees more of that. So this is more or less like 60 degrees west of north, or 30 degrees south of west, or south of west as well. That'd be another way of saying it. So I'm going to draw a coordinate system here again. Okay, so there's my coordinate system. That's pretty close to the line. But this one has to be 4 centimeters long, and it has to be at 240, which, like I said, is 30 degrees down from the west axis. So that's another way I can draw it. So putting my zero, or my center of my protractor at the end of that vector, and then drawing an angle of 30 degrees downward gives me this dot right here. So actually, it should be the corner. It just made that into a square, but I saw roughly where it went. So at this point, I'm going to take a 4 centimeter. And actually, before I do that, I'm going to have to move these because I see already that my vector is going to come into this area and make a problem. So let's paste it here. That should be enough there. Okay, so now I've got, oops, I already moved this. I should have drew that line first because I already erased the circle. All right, I'm going to do it again. I'm going to make another 30-degree mark. And I am staying faithful to the end of the vector as opposed to the origin that seemed to miss it a little bit. So if you see it seeming to look a little funny, that's why I'm going to make the mark here this time. So that's supposed to be 40 newtons there, and that would be 4 centimeters. So I'm going to draw a vector from the head of the purple vector to this one. And it's unbelievable how hard this is. The surface of an iPad is so slippery. Okay, and now cutting it down to 4 centimeters means it should end right about there. Okay, so I know graphically speaking, the actual resultant should be this vector in black, which I'm drawing now. And according to my measurements, this vector seems to be at an angle of around 49 degrees. So I'm saying this angle right here is about 49 degrees. And that's just from me eyeing it with a compass on top of my iPad. And the vector length appears to be from the origin here appears to be about 4.49 centimeters, which means that by scale, that should be 44.9 newtons at, now I'm going to say 49 degrees south of west. So that's what we're pointing at as our resultant. But let's now check this because we need to add them graphically. So first off, I'm going to look at the red vector, and that's vector A. And that one was at 45 degrees, and the length was 20, no, 14.414. So that means this x component is going to be positive, and the y component is going to be positive. And I get, using sine of 45 degrees is equal to a sub y, because that's opposite, over 14.14 newtons gives me AY is equal to, notice I'm forcing the sign here. I'm actually writing in the sign. I'm taking 14.14, multiplying that by the sine of 45 degrees, and that gives me really close to 20.0 newtons. And taking the cosine of 45 degrees, which is adjacent over hypotenuse, that's A sub x over 14.14. So A sub y, or excuse me, so A sub x is again positive, and we know that this is in fact going to be 20.00 newtons. So we figured out that one. Now, vector B, we have it going like this, and the angle that we found was B was supposed to be 20 newtons at 30 degrees south of east. So this angle is 30. And from this, we can see that the x component is still positive. That's why I drew it green. But the y component is negative. That's why I drew it red. So the sine of 30 degrees is equal to opposite over hypotenuse. And in this case, that happens to be the y component. So this would be by over the magnitude, which would be 20.0 newtons. So B sub y is equal to negative. Notice I forced the negative there. 20 times the sine of 30, and that gives me 10.0 newtons. And cosine of 30 degrees would give me B sub x over 20.0 newtons. So B sub x is going to be positive 20 times cosine 30, and that gives me 17.32. I can do the same thing with vector C, which is the purple one, and the purple one has a negative y component and a negative x component. And according to that, that one was supposed to be at 53.1 degrees west of north. So this angle in there is 53.1. So I want you to make sure y'all can do this on your own. I'm going to tell you that the x component is, I'm going to take the magnitude of that, which was 25.00 newtons. Actually, I should do this in purple anyways. So the x component was 25 times the cosine of 53.1, and that gives me 15.01. Y'all should be able to come up with this and the y component on your own. The y is also going to be negative, and that one should be given by sine. So I'm taking 25 times sine 53.1, and that one gives me negative 20.0 newtons. And then we can see the green vector. And in that case, that one was supposed to be uh, 240 degrees. So that made this, let's do this one as if it's 60, even though it's 30 this way. But I find it easier to do 60 the other way. This has both a negative y component and a negative x component. And what we can see is d sub x should be given by 40 times the sine of 60 degrees. And that gives me 36.64 negative. And d sub y gives me 40 times the cosine of 60, and that gives me 20. So now all I have to do is add the x components. So r sub x is equal to a sub x plus b sub x plus c sub x plus d sub x. And r sub y is equal to a sub y plus b sub y plus c sub y plus d sub y. So I can now compute that r sub x, and you guys follow me up on this. Make sure y'all agree with me. So my a sub y, or a sub x, was in fact positive 20. My b sub x was positive 17.32. 17.32. And then my C sub X was negative 15.01. So I just do minus 15.01. And then my D sub X was minus 36.64. So I'll just say minus 36.64. And that gives me negative 14.33 newtons. My R sub Y, I'm going to take the A sub Y, which is 20, and then I'm going to take the B sub Y, which is negative 10, so I'm going to say minus 10, and then I'm going to take the C sub Y, which is negative 20, so I'm going to say minus 20, and then I'm going to take the D sub Y, which is also minus 20, so I'm going to say minus 20, and that gives me negative 30. Now, that should also be the horizontal distance, 14.33, and the vertical distance downward. And if I look at the actual measurement just to see how good we are, the x component should be about 14.33, which would be 1.43 on here. That's not the greatest, but we'll figure out what it is. Now, all we have to do is take the magnitude of r to be the quadratic formula. I am adding all the decimal places. I'm just trying to not show it all because of the paper space I have. So I'm going to say 30 squared plus 14.33 squared. Did anybody verify my addition, by the way? I got
Yes.
1,100. Thank you. Good. I got 1,105 for the magnitude squared. So now I'm going to take the square root of that by raising it to the 0.5 power. And that gives me 33.25 newtons is the magnitude. We got 4.49, so that's not that great. But that's also because I was working on a slippery surface. Now the angle, that should be given by tangent inverse of the y component. And I'm taking the signs out. I'm not using any signs, but I'm going to take the y component, which we found above was 30, and divide it by the x component, which we found above, which is 14.33. And that should give us our degrees that I thought was about 49. So I'll say shift tangent inverse, parentheses, 30 divided by 14.33, close parentheses, and that gives me 64.47 degrees. So the actual algebraic answer is R is equal to 33.25 newtons at 64.47 degrees south of west. So that is how you add vectors. Something else that's kind of handy is we imagine. Does anybody have any questions on this first? Let's before I go on any further with that. I have the chat window open in case anybody needs to type them, but I'm listening for questions too. So something else your book does that you probably didn't have in you might have had it in your pre-calculus, but it's something called a unit vector. So what what we've done to make things a little easier and not have to write, at and all that stuff every time, you can actually represent a vector using what we call unit vectors. Now, a unit vector is a vector that's 1 unit long, meaning it's really like a pure number, except it has a direction. There's one called I hat. And I usually put a dot in it. I hat has a magnitude of 1 and points in the positive x direction. And then there's another one called j hat, and that points in the positive y direction. And then there's another one, k hat, that points in the positive z direction. So we could actually represent r as negative 14.33 newtons I hat minus 30.00 newtons j hat. And that too is another way of writing the answer. Okay, so that's just a very convenient tool. Not only that, if someone, like if I gave you a vector instead of giving it as some magnitude at some specification of the direction, like I did with these four here, if I gave them to you instead with like some number like 3i plus 4j, that's a lot easier to add to another vector that's like I minus 7j or something. So I'll show you that really quickly just to let you know how easy that is. So
Wait,
if we
wait, sorry.
go ahead.
Before we go on, I
Hmm.
just have a question about vector C
Yeah.
because I kind of joined late, but I'm looking at it and it says 53.1 degrees west of north, but
Ah,
isn't the
I
direction
did
it's
it
going
west of
in?
south. Yeah, I did
Yeah,
it west of
that's what
south.
I was wondering about. But the math is still the same, right?
Yeah, yeah.
Yeah, okay.
Yeah, thank you for that. Let's call that west of south. That way it'll be correct in your notes. I was wondering what was going on because I thought I had copied it, but in the heat of thinking about what's going on in the classroom, there's a danger that you sort of screw up. So I'm just going to change that to west of south. But normally I give you vectors in all four coordinates or in all four quadrants. And I was wondering why I didn't have one in there, but now I see why, as I misread the west of south for west of north for west of south. And I actually didn't even do that. I literally, I think I said the right number. I just drew it the wrong way. So be careful of this. Let me specify again what this all means. So just in terms of this, if we had this vector, this is E of north, whereas this is north of E. Similarly, if we had a vector down here, this vector would be south of east, and this angle would be east of south. Oops. Oops. Went to an eraser all of a sudden. If you had a vector in this quadrant, this would be west of south, and this would be south of west. This would be north of west, and this would be west of north. So that's the way that works. Another representation, by the way, just so everybody's on the same page and understands what we're talking about. This is also just called 45.00 degrees because I measured it counterclockwise from the positive x-axis. I could just write positive 45 degrees and you automatically know what that means. I could do this one, and if I measure it down like here, then this would be negative 53.1 degrees. That again is that notation that we use from our trig classes and stuff like that. Specifically, if you measure counterclockwise from the positive x-axis, you get a positive angle. And if you measure counterclockwise, you get a negative angle. So another example of this might be, for instance, here, in which case we could say this angle right here is 90 plus 45 is what I'm going to call it. So that's 135. But it's negative because I went counterclockwise. Or excuse me, because I went clockwise. Similarly, we could do this one right here. And in this case, we're saying, let's do this purple line. This would be 100 plus or 90 plus 53.1, so that'd be 143.1 degrees. Okay, so that's all those things. This would also be for compass headings, this would be 45.0 degrees compass heading. This one down here would be 90 plus 53.1 would be 143.1 compass heading. This one over here could be that's 45 plus 180, so it'd be 225 as a compass heading. And this green one would be this 270 plus 36.8 gives me 306.8 compass heading. Okay, so hopefully between that and these examples, you have some understanding of how we're going to specify vectors direction in the various ways that we specify it. And does anybody have any questions on how I drew that out and any misunderstandings or something you're not something you might be confused by on this?
One more time, what does CH stand for?
Compass heading. And I would normally write at a compass heading. I won't actually abbreviate it like that. I'm just trying to save space on the little iPad screen. So yeah, I actually drew the C vector in the wrong direction. That was supposed to be west of north instead of west of south. So that's why I didn't have a component in there. But it also helps you to remember the sign convention. So with x comma y, in this case, the x is negative, but the y is positive. Over here, they're both positive. Down here, they're both negative. And down here, the x is positive, but the y is negative. So those rules that you might have memorized at one time, I hope you never ever take the time to memorize them again. But you should come up with these results every time, so you can at least check them with these signs. If you have a vector that's in the first quadrant, both x component and the y component have to be positive. If it's in quadrant 2, it has to have a positive x and a negative y. If it's in quadrant 3, it has to have both negative components. If it's in quadrant 4, or excuse me, I said that backwards. No, I did say it right. If it's in quadrant 4, it'll have a negative x and a positive y. Any questions on that? So let me show you how easy vectors can be with this vector notation. And I'm going to show you an alternative version as well. Let's say A is equal to 3.0 I hat plus 4.0 j hat. And let's say B is negative 7.0 I hat plus 7.0 j hat. Then A plus B is just equal to negative 4.0 I hat plus 11.0 j hat. And we could have units on that, or it might just be a pure number addition thing, in which case we did that as well. Another notation, by the way, is I could say A is equal to 3.0 x hat plus 4.0 j hat, and B would be negative 7.0 x hat and 7.0 y hat. And then, of course, if you add a z component, it would be z hat instead of k hat. So that's another type of notation. If we wanted to subtract a minus b, that's defined to be a plus the opposite of b, and therefore that is a, which is 3.0 I hat plus 4.0 j hat, plus, now I'm going to write the opposite of b, so that's going to be positive 7.0 I hat minus 7.0 j hat. So 3 plus 7 are my x components. That's going to make 10.0 I hat, and 4 minus 7 is going to make minus 3.0 j hat. So that's how you compute a minus b. If you wanted 3a, that would be 9.0 x hat plus 12.0 j hat. And if you did negative 2b, that would be
I'm sorry,
uh
I have a really quick question.
mhm.
So, would it be X hat and Y hat, or would it just be X and J hat?
Oh, I see what you're saying because I mixed them up here. Yeah, I didn't mean to write that as a J. I meant to
Okay.
write that one as a Y, but I forgot I'd done it on the other case. So yeah, if you mix them up like that, I would never take off for that because that's just something careless. But yeah, I should have called that Y hat. And this one I'm using I's and J's, so I'll try to remember to stay I's and J's. Notice I multiplied negative 2 times 7 and got positive 14. Now I'm going to multiply negative 2 times positive 7, and I'm going to get negative 14.0 j hat. So, yeah, that's probably why I wrote the j hat over there, is because I was thinking about doing the negative 2b in I hats and j hats. So now you've sort of seen all the things that you can do with the addition or subtraction of vectors that we've talked about, as well as multiplying by scalars. Notice that when I multiply by a scalar, each component gets distributed the multiplier. So I didn't let the 3 just hit the 3 in front of the x hat. I let the 3 hit the 3 in front of the x hat and the 4 in front of the j hat. And that's how I got 9 and 12. Any questions on that? Okay, so I highly recommend you look over my videos of the world's best vector problem or whatever, and that should be fairly helpful to you. And now I'd like to get into projectile motion a little bit. Anybody have any questions on this before we go? So this should be more than sufficient for you to know how to do all the vector addition problems and subtraction problems. I will say there's also a quantity called the equilibrant. Equilibriant is another way of saying it. Equilibrant or equilibriant. That's the vector that you add to another vector to make it become zero. So it turns out, for instance, if we were actually covering this, we skip the statics section when we cover 241. But if you went in and covered statics, then what you'd find out is when you have 3 or 4 or 5 vectors adding on something, they have a resultant. And then if you're trying to make the net force on it be zero, then you'd want to add to that resultant the equilibrant or equilibriant, and that vector would just be sort of the negative of the resultant. So keep those words in mind because they'll pop up from time to time. Resultant and equilibriant. And equilibriant. Let's say the resultant is R and the equilibrium is E, then E is equal to the negative of R. So hopefully that helps you remember it. Now, the biggest, most important thing to remember about projectile motion, which is what we're going over now, the biggest, most important thing to remember about projectile motion is that the X and Y components of velocity and acceleration are completely independent. The best picture I can show you of that is let me pull up this image from the book real quick. There's an image, and it appears in every physics book when you start to cover uh, projectile motion. And it's basically a red ball and a yellow ball. One ball is fired horizontally at the exact same time. Another ball, the other ball, is dropped from the exact same height. And that is the perfect model to show you that X motion and Y motion are completely independent of each other. I'm almost there, pulling it up now. Going to the textbook, going to chapter 3. Now I'm going to go ahead and share my screen with you guys so you'll know what I'm looking at. Oops. Okay. That's weird. What the heck? Oh, okay. I went to the wrong area, but that's not a big deal. Now I'm going to go over here. This is where I want to show it to you. There should be a photograph here. Here it is. So what this is if you open the shutter on a camera a bunch of times in a couple seconds, what you'll see is this red ball and this yellow ball. The yellow ball was shot horizontally at the exact same instant the red ball was dropped vertically. And what you see at each interval, the red ball and the yellow ball are exactly the same height. That's showing us that gravity acts vertically on the red ball exactly the same way that it does on the yellow ball. Even though the yellow ball was shot horizontally, and it even does that when you fire it instead of horizontally. If you shot it up vertically, what you'd find out is the y component of that velocity, even while it's going up, is going to decrease by 9.80 meters per second each second that it goes up if we ignore air resistance. That means if you only did a tenth of a second, it would change its velocity by 0.98 meters per second every second. And if you did it a hundredth of a second, it'd be 0.0980 meters per second every second that it slowed down, slowed down, slowed down. And then once it got to its top, it's going to continue to lose velocity, and that velocity on the way down is going to be negative. So you're actually increasing the magnitude by negative 9.8 each second, or negative 0.98 meters per second, each tenth of a second, or 0.0980 meters per second, each hundredth of a second. So that picture says it all. And what we need to remember is our actual kinematic equations, which we had basically average speed was distance divided by time. Average velocity was delta x over delta t. The instantaneous velocity was dx over dt. The average acceleration was delta v over delta t, and the instantaneous acceleration was dv dt, which is d2x over dt squared. But we also got x is equal to 1 half at squared plus v0. I'm going to put an x on it now because we're dealing with motion in
I'm
two
sorry.
dimensions.
Are we
Just letting you
supposed to
know.
be seeing
Yeah, we're still
something
looking at the
on the
Oh,
textbook.
thank
screen?
you. Thank you. Yep. I did want to change that back. I just forgot to. Here you go. This white hair is looking really old, ain't it? Thanks for reminding me, everybody. Here we go. iPad. That should pop up now. Yeah, I guess if you're looking at my old bald head, this is what I'm writing. I should probably be thinking, oh, maybe I should share the screen with them. They'll really like that. Okay, so the difference here is I am writing the kinematic equations, and I got one more term right on this one, plus x zero. Then we had, of course, v equals v zero plus at, which now in two dimensions, we're going to have to call this like that. And then we also have v squared is equal to v zero squared plus 2a x minus x zero. But the whole purpose of me telling you this is we can now write y is equal to 1 half a sub y t squared plus v zero sub y t plus y zero, and v sub y in this case is equal to v zero sub y plus a sub y times t. And then you could even write v y final squared is equal to v sub y 0 squared plus 2a sub y minus y 0. And this should actually have an x on it. So that's sort of the way you can use kinematic equations now, because you have a set for the y components and you have a set for the x components. And in fact, we normally call a vector that points to its position in space. Some books will call it x. I call it r just because r doesn't mean x, doesn't mean y, doesn't mean z. In cylindrical or in polar coordinates, it means basically the distance away. So it's very reasonable to do that. We're going to say this is r of t, and the most general form, of course, would be 1 half a sub x t squared plus v zero sub x t plus x zero times I hat plus 1 half a sub y t squared plus v zero sub y t plus y zero j hat. So that is the most generic expression of position as a function of time, assuming it's only two-dimensional. If it's three-dimensional, we have to add a third one of these. But this also is allowing an acceleration in the x direction, an acceleration in the y direction, an initial position other than the origin, and all that good stuff. So you can see that. But when we actually do projectile motion, it would be better to use this. In this case, you normally write R. And for projectile motion, we're talking just like a free body, like we did at the end of chapter two. In free fall, I said free body. In free fall, the acceleration's supposed to be a constant. It's downward. It's negative 9.80 meters per second per second. If we choose upward as a positive direction, we call that negative 9.8. But really, the magnitude is 9.8 meters per second every second. And normally we ignore air resistance so for projectile motion, so that means that acceleration is right, and instead we're going to get v0 times t times cosine theta, where theta is the launch angle. So we're saying, like, here's a cannon, here's a bullet flying out, this angle is theta, like that, and this velocity is v0. So that's v0t cosine theta plus y0, all of that times I hat. And then plus, in this case, we have negative 1 half gt squared, because I've automatically just chosen, and I don't have to, you can change this, but this is what we often do, is we normally just assume up is the positive y direction and right is the positive x direction. And we write, and that was supposed to be a y0, I mean an x0, not a y0. Feel free to tell me I did something stupid. I'm okay. I completely appreciate it. So, 1 half GT squared plus V0 T sine theta plus Y0 and all that in the J hat direction. Okay. If we start with that, it's kind of neat because we can see that velocity, which is supposed to be dx dt, but now it's not just an x thing. So we can say that v of t is dr over dt. And what you can see is this is going to give us a v0 cosine theta I hat plus negative gt plus v0 sine theta j hat, and that's the velocity. And then a of t, which is dv dt, becomes negative g times j hat. That's it. So that's a way you can do everything completely with vectors, not thinking too much about it, and so on. So let's look, since I got a little bit of time, I'm going to sort of do a generic vector problem, a generic projectile motion problem like this. Let's say we have this fired from some height h over level ground once you get off this cliff. And I'm going to draw a little cannon right here. And actually, I'm imagining the cannon as if it's actually under the ground, in which case I could change this. This would be a little better for me. I could change this to the actual projectile that's being fired. And the path it's going to take, we know, is roughly a parabola like this. This is y max. And in fact, right here at the end, we have v final as a vector quantity. And I'm going to assume my x-axis is this way. And I'm going to assume my y-axis is this way. And the origin is directly under where it started. So I can immediately write that r of t is actually equal to v0. And remember, this is the v0 vector at angle theta. So this would be v0 t cosine theta, and there's no x0 in this case, so I'm just going to write I hat plus negative g, oh, negative 1 half g, sorry about that, I forgot I wasn't doing the velocity one now, negative 1 half g t squared plus v0 t sine theta plus h j hat. Now, that is the way you can do it, and you can work through the vectors this way by taking the derivative, get the initial velocity, get the velocity as a function of time, and then take the second derivative, get the acceleration as a function of time, all that good stuff. But at the end of the day, we want to know things like time aloft, or you might call it hang time in terms of an NFL or college football punt. That would be the hang time. H max, this distance is actually called the range. And that's normally meant for an object firing from the same height that it lands at. But generally speaking, you could just say range is how far away it's going to fall. With this one in mind, let's say V0 is equal to, uh, let's say 40.0 meters per second at 30.0 degrees. Then we could say R of t is equal to 40 times cosine 30 gives me essentially 40. Whoa. Oh, no wonder. 40 times cosine 30. I knew that wasn't right. Uh, that is 34.64. So 34.64 meters per second times t I hat plus negative 4.90 meters per second t squared plus 40 times sine 30 gives me 20 meters per second times time. And let's say h is 50 meters. So I'll say plus 50.00 meters. And the j hat goes in there. There is a shorter way too, by the way. You can just write it like this, and it'd be 34.64 meters per second t and negative 4.90 meters per second squared t squared plus 20.0 meters per second t plus 50.00 meters, like that. When I use less than and greater than symbols, that's the same thing as using I hats and J hats. If you put a third spot, that would be for the K hat as well, but that's a lot easier way to write it. Now, with all that information, we can go ahead and figure out, like I said, what the velocity is at any time and all that good stuff. So let's take V of t. This is just the derivative. So writing it in this new simpler way, we get 34.64 meters per second is the velocity in the horizontal direction. That's a key thing to learn. That's sort of the point. If you ignore air resistance, then the shadow of the ball that you throw is going to move at a constant speed horizontally on the ground. The vertical motion is going to be different. It's going to decrease, 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 come to a stop, then speed up, down, speed up, down, speed up, down, speed up, down, speed up, down again. So we've figured out already that the x component of velocity is never going to change. In this case, we're going to get negative 9.80 meters per second every second times t plus 20.0 meters per second, like that. So we can see immediately, for instance, that the V0, which is V of 0 seconds, is in fact 34.64 meters per second, comma 20.0 meters per second in the j hat direction. Now, what we could do is say, I would like to know at what time this projectile hits the ground. So time aloft implies set r sub x equal to 0. Or excuse me, r sub y equal to 0. R sub y is the vertical one. So what's going to happen is, remember, the x velocity is going to just stay 34.64, 34.64, 34.64, but the y component is going to get smaller, 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 smaller. And in fact, in 1 second, it's going to go from 20 to 20 minus 9.8. In 2 seconds, it's going to go from 20 to 20 minus 2 times 9.8, which is 19.6, so it's zero point 0.4. And then, a fraction of a second later, it's going to be at zero velocity. A fraction of a second later is going to be negative 19.6, and so on and so forth. And it's going to continue down like that. But if we set r sub y equal to 0, then we can solve for time. So if I set r sub y equal to 0, that means negative 4.90. I'm going to leave the units off because it gets nasty. Times t squared plus 20.00t plus 50.00. All that's got to be equal to 0. And this is very typical. You're supposed to know your quadratic formula. So negative b plus or minus square root of b squared minus 4ac over 2a. So that tells us t is equal to negative 20.00 plus or minus the square root of b squared. So that's 20.00 squared minus 4 times a, which is negative 4.90, times c, which is positive 50.00, negative b plus or minus square root of b squared minus 4ac over 2a. So 2 times a would be negative 9.80. And you can work out the units. You'll see it does work out to be seconds, but I'm first going to take what's under the square root because that's our discriminant. So it'll be minus 20.00 plus or minus the square root of 20 squared plus 4 times 4.9. Notice the negative times a negative gave me positive times 50. That gives me 1,380. And you can see that that would be in units of meters squared per second squared. And then all this is divided by negative 9.80 meters per second per second. So you see that once I take the square root, I'm just going to have seconds on the top. Square root of 1380 is 37.14, so it's going to be negative 20.00 plus or minus 37.15 technically. Actually, I should call that 148. That way I'm carrying an extra digit. All that divided by negative 9.80. Now, negative time doesn't make any sense, so if I took the negative sign in the top, you have a plus over top of a minus. If I did that minus, that'd be negative 20 minus 37. That gives me a huge negative number. But then I'm dividing it by negative 9.8. So that actually gives me a good size positive number. So that's one of our choices. So I'll say negative 20 minus 37.148. And now I'm going to divide that by negative 9.8. And that gives me positive 5.831 seconds. Now, we would have 4 sig figs after the subtraction in the numerator. So that's okay to 4 sig figs, and this would just be seconds. Now the other one would be negative 20 plus 37, and then you divide that by a negative. The 37 minus 20 clearly gives you a negative quantity, or excuse me, it clearly gives you a positive quantity, but then dividing by a negative would give you a negative time. And that actually has a physical meaning. But the meaning is if you imagine what projectile would be fired from ground height, such that when it got to the height of 50 meters, it would go right through that point on the y-axis where this projectile went, and it would have exactly that velocity v0 there. Okay. But it wouldn't be V0, it wouldn't be the same initial V0. It would be a new velocity at that particular time. So that's what the negative time interval would be. So to show it to you, for instance, negative 20 plus 37.148. Uh, Now I'm going to divide that by negative 9.8, and that gives me negative 1.7498 seconds. So you could actually figure out a calculation that would show a projectile launched from the ground 1.7498 seconds earlier would actually come at 1.7498 seconds, would arrive at our spot that I drew right here. After that many seconds, that's where it would be, and it would have exactly this velocity that I specified, and it would follow this trajectory and land over here. So what we do have is the time aloft. So I'm going to say time aloft is equal to about 5.831 seconds. Now, with that in mind, you can also find out how far away did it land, because the x position is just 34.64 times time. So let's call this x max, because that's the maximum distance it got horizontally before it hit the ground. And x max is just going to be 34.64 meters per second times 5.831 seconds. So if I take 5.831 times 34.64, I get 201. Might as well say 202.0 meters. So that's how you actually could find out the distance you traveled. If I wanted to figure out my max height, Y max, I say V sub Y equals 0. That's what I need. V sub Y equals 0. And remember, if I look at the V, I see that that's negative 9.80 T plus 20. So negative 9.80 meters per second T plus 20.00 meters per second equal to 0. I can see that T is going to be equal to 20 divided by 9.8, and that gives me 2.041 seconds to max height. That could be a question that I'd ask. After how many seconds will it reach its maximum height? That would be how I'd ask that. But what I'm trying to figure out is Y max. So now I need to plug that time into Y. So now we plug this time into R sub Y, because R sub Y is the height at any point in time. So if I substituted it at that time, it should be the height it has at the 50 meters, at whatever that height was above the 50 meters. So now I'm going to take and set this y component, which is negative 4.90. I'll leave off the units again. 4.90 T uh, plus 20.0 T, and I think it's plus 50. Yes. plus 50.00. This is r sub y of t. And now all I have to do is plug that in and say r sub y equals, uh, let's see, r sub y at time aloft equals y max. So r sub y of 2.041 seconds is going to be negative 4.90 meters per second times 2.041 seconds squared plus 20.00 meters per second times 2.041 seconds plus 50.00 meters. So this is going to be negative 4.9 times 2.041 squared. This gives me negative 20.411 meters plus 20 times 2.041. That's easy enough, 40.82 plus 50.00 meters equals. So when I add all these, I get 61.23 meters equals Y max. So I've now shown you how to find the time aloft. I've showed you how to find the X max, which once you have the time aloft, all you have to do is multiply the X max times the Y or the X component of velocity, and that'll give you how far along it goes. And you can even figure out the final velocity. So V final equals question mark. Well, all we have to do is find out uh, Vy of time aloft. So all I have to do is take my equation for the velocity in the y direction, which is Vy of t is equal to the negative 9.80 meters per second t plus 20.00 meters per second uh without that, sorry about that, like that. Now I can say V final sub y is going to be equal to negative 9.80 meters per second times 2.041 seconds plus 20.00 meters per second, negative 9.80
I'm
times two.
sorry. I
Yeah.
think you have the wrong T. You have the T for the max height and that V final
Okay.
instead of the time aloft.
Let's see. So V sub y negative 9.8. Uh, are you talking about the stuff I wrote in the blue or the stuff I'm doing right now?
I was talking about the T that you're just plugging in
Okay.
now.
Oh, that's the max height. Okay, thank you. Yeah, good. Glad that you caught that because we did solve for the right one. I just grabbed the wrong one. Nice catch on that one. The time over here is 5.831. Thank you for that. That's exactly what I need. 5.831 seconds. So ignoring, of course, sig fig's issue. So I get negative 57 for the multiplication part, and then I got to add to it 20. So I get negative 37.14 meters per second. That's just the y component. The reason why we only did the y component of velocity is because the x component of velocity stays the same the whole time. The x component of velocity is 34.64 meters per second, as this shows right here. This is V of t, and that's always that. So that means V final as a vector is 34.64 meters per second, and then negative 37.14 meters per second in the y direction. So that's the vector. We could leave it like that, or we could write V sub f is equal to, now I'm going to take 34.64 and I'm going to square it, and I'm going to take 37.14 and I'm going to square that. And now I'm going to take the square root of all that, which by the way came up to 2,579. I'm taking the square root of that. So it's equal to 50.79 meters per second. And it's at plus 37.14 squared. That's how I got that. Theta equals the inverse tangent of the y component, which is 37.14, over the x component, which is 34.64. So when I do the inverse tangent of that, I get shift tangent inverse 37.14 divided by 34.64, close parentheses. That gives me about 47.0 degrees. And that is below horizontal. So that is another way of expressing our final velocity. This is another way of expressing it. And now we've sort of gotten pretty much everything that you could be asked for on projectile motion. And we did that in the general case. Additionally, I set up all the equations just in terms of V0 and theta, but I also worked it out without with actual numbers and did it for something that's being fired off a cliff and landing at an entirely different height. So I've shown you time aloft, I've shown you X max, which I should probably box off as well. So we got that. I got the time to max height, and then I got the max height as a distance, and then I got the final velocity. So that's sort of the trick. You don't have to use any of this vector stuff. I'm just showing you how you could have used it. At the end of the day, you're just using the quadratic, or excuse me, occasionally you use the quadratic formula, but you're just using the kinematic equations. Anybody have any questions on that? So let me show you a way without the complexities of the vectors. We're going to again assume that there was this little cannon firing right here, and that caused the projectile to leave with a velocity v0 at an angle theta. Now that's going to result in a parabolic arc where this is the range, this is y max, and this is t hang time, which I called time aloft before. That's something we should know as well. And we also need to know V final. So those are typical things we would solve for, is the range, R, and stuff like that. So let me show you how I'm going to do this. I know that V0 is equal to V0 cosine theta I hat and V0 sine theta j hat, but all I really care about is V0 sub x and V0 sub y. So in this case, it's just going to be V0 cosine theta, and V0y is going to be V0 sine theta. Now, if I want to find out how long it is for hang time, so let's say hang time. Let's figure out that part first. What I want is the y equation equal to 0. I know the kinematic equation for y is y equals negative 1 half gt squared plus v0 t sine theta, and then plus y0, but I started this at the origin, so there is no y0. So if I set y0 equal to t, or y equal to 0, I get 0 is equal to negative 1 half g t squared plus v0 t sine theta, which you can also write as t times negative 1 half gt plus v0 sine theta. So this is true when t equals 0, or when t is equal to 2v0 sine theta over g. So what I have here is the generic formula for the hang time. And if you can just use that, if you happen to memorize it, you can use that to find the hang time at any problem, as long as it's shot from the exact same height that it is landing at. Then this equation works. Katie said she got 70.41 for Y max, and I got what? 61.3. That could be right. I explained how I did it. If you find a mistake on it, that's great. But everything I said and all the equations I wrote were proper. It's just it might be a matter of maybe I made an arithmetic error, or maybe I like I did with the time, I substituted the hang time instead of the full time. So that or the time to the max height instead of the hang time. So that could be the problem. But other than that, it should be done correctly. Thank you for. You think I forgot square t at first? Yeah, that could have been what happened. Uh, oh, we didn't need a square t because we drive. Yeah, yeah. When you took the derivative, you got rid of one of the t's. So, anyways, so that's just a generic way to find out the hang time. Now we can still use that hang time to find out the range. So again, when we're talking horizontal, from same height to same height, that is the technical definition of range. So now I'm going to say range. To do that, R is just V0x times T hang time. And actually, I should probably put a HT down there just to remind everybody what that is. So in this case, I'm going to say the x component of velocity is V0 cosine theta, and then I'm going to multiply that by 2 V0 sine theta over g, and you can see that r is in fact going to equal 2v0 squared sine theta cosine theta over g. And it turns out there happens to be in the back cover of the book, they actually have a lot of valuable stuff like trig functions, trig identities, all sorts of good stuff like that. And there is a trig identity associated with this one, and that is the sine of 2 theta. Let's write this in a different color so you'll know it's a sidebar. The sine of 2 theta is equal to 2 sine theta cosine theta. And there's a really good reason for me taking time to do this. The r, therefore, just becomes v0 squared sine of 2 theta over g, and that is our range formula. And not only that, the fact that that's 2 theta, and when you're doing projectile motion, it doesn't make any sense to talk about an angle bigger than 90 degrees. So we're really only focusing on the first two, the first 90 degrees of the graph of the trig functions. So for instance, if we looked at sine and theta only up to 90 degrees, what you'd see is the sine, which normally goes max height 0 max negative height 0, but this part is 180, this part is 360, and this part is 90. But when we graph y equals sine of 2 theta, then we basically get a graph that comes up, but actually finishes it all in half the time. So what we're going to imagine is it goes up here and then down here, only now this is 360 and this is 180. And actually, I said that sort of the wrong way. The main thing I'm trying to show you here is because of the angle being 2 theta, then 0 to 90 is all that makes sense, but 90 is now going to look like just this. So that's our 90-degree mark. That's theta, and this is y equals sine of 2 theta. Okay, so that means unless you're going for the absolute maximum by firing at 93 degree, 90, excuse me, at 45 degrees, then you're going to have two different angles that work. You're going to have a low angle and a high trajectory. You've probably seen that some of the better free throw shooters in basketball usually shoot it with a good arc to it going a little high. Whereas if you look at like Shaquille O'Neal, who was notoriously bad at free throws, he's so darn tall, he just sort of shoots it almost diagonally. He has to shoot up a little bit, but it just barely goes like that. And it's really a low probability shot because if it's not exactly on the mark, it's going to bounce off the back of the rim, the front of the rim, or the back of the rim, then the front of the rim, and all sorts of stuff. Whereas if it's got a lot more room for error when you shoot in the high trajectory because it's coming down, and technically you can fit two basketballs diameter in to diameter in the actual rim. So that's how big that hole is. So you have a range of basically a whole diameter that you're able to hit inside of there, and it's still not miss. That's because it came from that high angle instead of that low angle. But this sine of 2 theta is what shows us that there's two trajectories. And it also shows us by that graph at the bottom that they should be an equal distance from 45 degrees. So for instance, if you find a trajectory that is working at 40 degrees, to make a free throw, for instance, then you can also shoot the same ball at, instead of 40 degrees, which is 5 below 45, you can shoot it at 50 degrees and get the same thing. Okay. In other words, it'll still hit, but it's the high trajectory now. Similarly, we could do 35 degrees, that's 10 below, and that would correspond to 55 degrees, that's 10 above. So those are your two motions there. If you actually wanted to figure out how big the y component of velocity is, so VF sub y, if you want that, that occurs basically when the t equals t hang time. So that's V sub y of t hang time. And of course, the V sub y was negative 9.80 meters per second times t hang time plus 20.00 meters per second. Double checking my equation that I got. Yeah, that should work. I just want to. Oh, it's not. Stupid me. I forgot I was doing the problem with the generics. So, uh, actually, let me get this a little bigger. I just literally slipped into doing the other problem. So in this case, we got Vy of TH. Well, V sub y was V0 sine theta, and then that's times T. So the V sub y in the, oh, excuse me. Oh, right there it is. So this is going to be the negative GT squared plus V0 cosine, oh, this is be sine, sorry. V0 sine theta And that was supposed to be an exponent of 1, not an exponent there, and there's no time on this one. So that should be that. But what I need to do is now plug in t hang time. So we have negative g times t hang time, and t hang time was 2v0 sine theta over g, plus v0 sine theta. You can see the g's canceling out already, and what we get is negative 2v0 sine theta. Don't Okay. Negative 2v0 sine theta plus v0 sine theta, which equals negative v0 sine theta, which was negative v0 sub y. So with the symmetry of a projectile that's launched from ground height and then lands at ground height at the exact same level, then you see that the y component just changes sign from the beginning to the end. So that means our final velocity, Vf sub like this, is actually V0 cosine theta negative V0 sine theta. And that's a fairly generic answer because it works for any theta as long as as long as the initial height and the final height are the same, then this equation applies as is. Any questions on that? All right. Well, that's it, folks. I've done a pretty good coverage of chapter 3. I'll still have more stuff to cover next time. Maybe I'll work some more examples that you might come up with, and then we'll start into chapter 4. You guys are free to go. If you didn't already chat me your first and last name, make sure you do, and have a good one. Thanks for coming, everybody. Don't forget your lab.
All right, bye, Professor.
See you, Zach. Feel free to stick around and ask questions if you have any.
Should we put any time into uniform circular motion?
Yes, yeah, that's going to come into play. We're going to re-examine it later, but that'll come into play. So I'll do something with that as well. We normally don't cover it until I was double checking to make sure it's not something in our in this chapter 3, but it doesn't seem like it is. So yeah, we won't deal with that until we get to the second chapter of Newton's laws. So it's like chapter 4 or 5, if I remember.
Okay.
All
Okay,
right.
cool. Thanks.
No problem. See you, Jesse. Anybody else?
I just need to talk with you.
No problem. Uh, Anybody else have any questions? All right, I'll do a breakout room. That'd be the easiest way we can do that. I'm going to stop sharing for a second. And now I'm going to find my Zoom channel and I'm going to create one breakout room. Aside, that was Liam that had to talk to me, right?
Yes, sir. Yes.
Okay. Okay, come on to the room, the breakout room, and we'll be talking there. I'm going to go ahead and